What is the universe? A divine artifact? A silent accident? Or something far more elusive, hidden behind the illusions we call knowledge? Since the first flicker of thought, we have stared into the endless black, weaving myths, forging gods, imagining patterns where there may be none. Every age has carved its own mask onto the unknown. Yet the true face behind the mask remains untouched, unseen. It slips through the fingers of reason, evades the prayers of the faithful, mocks the ambitions of the learned. The universe we speak of is not a thing we understand. It is a mirror, reflecting only the fragile dreams of humankind. Tonight, we step into the void between certainty and oblivion. Tonight, we tear away the comforting lies. Tonight, we follow the question that has no answer. Masks of the universe. Even our ideas about a name for the universe, everything, is part of it. Still, the universe itself is what? Are we really completely naive? It offers several sides and implies several different things to many other people. To religious persons, it is the theistically produced world governed by supernatural forces. To artists, it is an exquisite world revealed by sensitive perceptions. To professional philosophers, it is a logical world of analytical and synthetic structures. And to scientists, it is a world of controlled observations clarified by natural forces. Alternately, it can be all these things several times. Even more varied are the worlds of cosmic images kept by people from many civilizations, including the Australian Aboriginals, Chinese, Eskimos, Hindus, Hopi, Maoris, Navajo, Polynesians, and Zulus. Cosmic pictures change with knowledge and cultural contact. Consequently, in Europe, the medieval culture shaped by the expansion of Islam changed into the Cartesian, Newtonian, Victorian, and Einsteinian images. 100 years later, the Victorian standard Western global vision of the late 19th century differed totally from the Einsteinian one. Every civilization in every age creates a different cosmic vision, fit for the face of the future universe. When we discuss the universe, we have to differentiate the several models of the universe. Since everyone, religious, artistic, philosophical, or scientific, is one of many representations comparable to the models of many civilizations. Therefore, throughout the development of science, we have been split among the Pythagorean, atomist, Aristotelian, and so on. We should list the Pythagorean model of the universe, atomist model of the universe, Aristotelian model of the universe, and so on. Eventually, the models get the shortened names: the Pythagorean universe, the atomist universe, the Aristotelian universe. And we confuse ourselves by using the word universe to denote a model of the universe. The grandiose word universe has a further major disadvantage. When used alone without specifying the model we have in mind, it conveys the impression that we know the true nature of the universe. We find ourselves, in the company of multitudes of others in the past, speaking of the universe as if it were finally discovered and revealed. By referring to the contemporary model of the universe as the universe, we forget that our contemporary model will undoubtedly suffer the same fate as its predecessors. We always mistake the mask for the face, the model universe for the actual universe. Our ancestors made this mistake continually, and most likely our descendants will look back and see us repeating the same error. The Pythagorean universe, the atomist universe, the Aristotelian universe, and so on. Each universe is a mask, a cosmic picture, a model invented, modified as knowledge advances, and finally thrown away. We may avoid directly referring to the true nature of the universe, which we cannot guess even in our wildest imaginings. When used alone, as in such sentences as the vastness of the universe, the word universe denotes our present universe as revealed by contemporary science, free and loosely used without always reminding us that the universe is still mysterious and unknown. Continually ask yourself, what is the meaning of life? What puzzle does the universe present? Why did all of this start? How will all of it turn out finally? Are these related questions? The search is condemned to go awry from the beginning until we familiarize ourselves with the worlds of the past and especially with the present universe. Every one of us seeks the answer. Each of us repeats the words of Erwin Schrödinger. I know not whence I came, nor whither I go, nor who I am. Broadest sense, cosmology is a joint endeavor of science, philosophy, theology, and the arts seeking to understand what unites and is fundamental. It draws on knowledge from other sciences such physics and astronomy, and assembles a physically all-inclusive cosmic picture as a science, which is the main focus in this podcast. We explore the small-scale and large-scale domains of the universe. We delve deeply into the microscopic worlds of cells, molecules, atoms, and subatomic particles, and reach far into the macroscopic realms of planets, stars, galaxies, and the universe. We find that the minimal and the large are intimately related in cosmology. Daily, we deal with ordinary things like plants and flower pots. To understand these things of sensible size, we explore the small-scale and large-scale domains of the universe. Since the 17th century, knowledge has advanced rapidly, and the number of scientists has grown enormously. Each science focuses on a domain of the universe, and tends over time to fragment into closely related new sciences of greater specialization. Originally, the characteristics of living and non-living things defined the differences between the broad domains of biology and physics. As it advanced, these basic sciences branched into new ones, which in turn became more specialized. Physics, once known as natural philosophy, has grown and branched into high-energy subatomic particle physics, low-energy nuclear physics, atomic physics, chemical physics, condensed matter physics, biophysics, geophysics, astrophysics, and so on, and each has its theoreticians, experimenters, and technicians. Biology, once the subject of naturalists of broad interests, with associated sciences such as botany, zoology, entomology, ecology, paleontology, and so on, has grown and branched into molecular biology, biochemistry, genetics, and so on. And astronomy, once the subject in which everybody had equal knowledge, but not computing skill, has branched into planetary sciences, the study of stellar structure and atmospheres, interstellar media, galactic astronomy, extragalactic astronomy, and the separate fields of radio, infrared, optical, ultraviolet, X-ray, and gamma-ray astronomy. A person studying a branch of science in depth becomes a specialist, engaged in a maze of detailed knowledge, who knows much about a small domain of the universe and is rather ignorant of all the rest. The sciences split the universe so that each may build a domain of special knowledge in depth, often into smaller and smaller pieces. Unlike all other scientists, Cosmologists adopt a broad perspective. Unlike Impressionist painters, they keep a distance from their canvases to avoid too distracting details. Cosmology is the one science in which specialization is rather difficult. Its main goal is to assemble the cosmic jigsaw puzzle, not to study any particular piece in detail. Introductory cosmology is not a branch of astronomy. It is a cosmopedia, more than an inventory of the universe's content. The universe is not a whole universe catalogue of descriptive astronomical data. Cosmology is the study of the primary cosmic constituents, such as the origin and history of the chemical elements, space and time, that form the frame of the expanding universe. Large space regions scatter the primary things of importance and endure for long periods. The origin and evolution of stars and galaxies, even the origins of life and intelligence, are important cosmic subjects. Subatomic particles, their role during the earliest moments of the universe, and subsequent combinations into atoms and molecules that form the complexity of the living cell and our surrounding world, are all of cosmic interest. At each turn, the issues of cosmology cause us to pause and reflect. Many subjects of vital importance are still obscure, such as the acquisition of speech, the development of large brains, and the ability to create abstract mental structures and think quantitatively. What determines how humans think also determines the design they perceive in their universes. Human beings form a vital part of cosmology and represent the universe perceiving and thinking about itself. Who are the cosmologists? Professional cosmologists are relatively few. They are well versed in mathematics, physics, and astronomy, and study the evolution and large-scale structure of the physical universe. In general, however, people become cosmologists whenever they seek to understand the universe. When we stand back from the study of a specialized area of knowledge, or step aside from our everyday affairs and reflect on things in general, and try to see the forest and not just the trees, the whole painting and not just the dabs of paint, the whole tapestry and not just the threads, we become cosmologists. Cosmology is as old as Homo sapiens. It goes back to when human beings, living in primitive social groups, developed language and made their first attempts to understand the world around them. Hundreds of thousands of years ago, humans likely explained their world through various means. Spirits of all kinds, motivated by human-like impulses and passions, activated everything. The early people projected their inner thoughts and feelings into an outer, animistic world in which everything was alive. With supplications, prayers, sacrifices, and gifts to the spirits, human beings gained control of the phenomena of their world. It was the age of magic, of benign and demonic spirits incarnate in plant, animal, and human form. Ambient and indwelling spirits' passions, motives, and actions explained everything that happened readily and easily. It was an anthropomorphic world of the living earth, water, wind, and fire, into which men and women projected their emotions and motives as the guiding forces, the kind of world children read about in fairy tales. From this golden age comes our primeval fear of the menace of darkness, the rage of storms, and our enchantment with the wizardry of sunrises, sunsets, and rainbows. For reasons not yet fully understood, human beings everywhere remained one species, and cultures, languages, social codes, belief systems, laws, and technologies were interchanged. Possibly our moral codes of today, which regulate behavior in the family and society and determine in general what is ethically right and wrong, were naturally selected over long periods in primitive societies. Societies deficient in codes of mutual care and support among individuals had little chance of surviving. At the dawn of history, 10 or more thousand years ago, the early city-states ascended. More abstract concepts of the universe's magic evolved into the mythic universe, and the long age of magic led to what might be called the Age of Theism. The spirits that had been everywhere, activating everything, amalgamated, retreated into remote mythic realms, and became powerful gods who personified abstractions of thought and language. In The Golden Bough, James Fraser speculated on how magic among primitive people evolved into theism, and how the magic universe transformed into various mythic universes. With the growth of knowledge, man learns to realize more clearly the vastness of nature and his littleness and feebleness in the presence of it. However, recognizing his helplessness does not carry with it a corresponding belief in the impotence of those supernatural beings with which his imagination peoples the universe. On the contrary, it enhances his conception of their power. If he feels so frail and slight, how vast and powerful must he deem the beings who control the gigantic machinery of nature? Thus, among the more acute minds, religion gradually replaced magic, which explains the continuation of natural events as governed by the will, passion, or caprice of spiritual beings like kind man, though much superior to him in strength. The Sumerian, Assyro-Babylonian, Minoan, Greek, Chinese, Norse, Celtic, and Mayan mythologies, to name only a few, reflect mankind's earlier conceptions of the universe. Creation myths, often difficult to understand, are particularly interesting. Many mythologies have simple cosmic images. Men and women stayed safe and centrally relevant in an anthropocentric universe. People mostly occupied the center, around which the university gathered. The legendary gods continued to serve and protect human beings, regardless of their strength and distance. Anthropocentricity formed the basis of the Greek cosmology of an earth-centered universe. The universe of Aristotle in the 4th century BC was geocentric, or earth-centered. The spherical Earth rested at the center of the universe, and the moon, sun, planets, and stars, fixed to translucent celestial spheres, revolved around the Earth. The innermost region of heaven, the sublunar sphere between the Earth and the moon, contained earthly and tangible things in an ever-changing state, and the outer regions of heaven, the celestial spheres, contained ethereal and intangible things in a never-changing state. This system's subsequent elaborations, bringing it closer to agreement with astronomical observations, culminated in the Ptolemaic system of AD. The Middle Ages, 5th to 15th centuries, were not as dark as was once supposed. From the 13th to the 16th century, the medieval universe was perhaps the most satisfying form of cosmology known in history. Christians, Jews, and Muslims were blessed with a finite universe in which they had utmost importance. By the Arab and European standards of those times, it was a rational and well-organized universe that everybody could understand. It gave location and prominence to humanity's place in the scheme of things. It provided a secure foundation for religion, and it gave meaning and purpose to human life on Earth. Never before or since has cosmology served in such a vivid manner the everyday needs of ordinary people. It was simultaneously their religion, philosophy, and science. The transition from the finite geocentric universe to the infinite and centerless universe is known as the Copernican revolution. In the 16th century, Nicholas Copernicus crystallized trends in astronomical thought that had originated in Greek science almost 2,000 years before and proposed the heliocentric, or sun-centered universe. The Copernican heliocentric universe soon transformed into the infinite and centerless Cartesian universe, which, in turn, was followed by the Newtonian universe revolution in outlook that occupied the 16th and 17th centuries. The Copernican revolution opened the way for modern cosmology. But the spiritual university is vastly more important than the physical university, which is firmly anthropocentric. The spiritual universe is the great chain of being, a chain of countless links that descended from human beings through all the lower forms of life to inanimate matter and ascended from human beings through hierarchies of angelic beings to the throne of God. Humanity was the central link connecting the angelic and brute worlds. Even in an infinitely large physical universe, deprived first of the Earth and then of the Sun as its natural center, it was still possible to cling to old ideas that portrayed human beings as having central importance in the cosmic drama. The gods were ever mysterious, and after the Copernican revolution, they became more mysterious than before. In the middle of the 19th century came the most dreadful of all revolutions, the Darwinian Revolution. Humans, previously the central figures in the cosmic drama, began to resemble the creatures of the field. The gods who had attended and protected humanity for so long were cast out of the physical universe. The anthropomorphic, magic, and anthropocentric mythic universes were wrong in almost every detail. The medieval universe and the concept of the great chain of being have been discarded. Finally, science triumphs, dispelling the myths and superstitions of the past. We applaud the Renaissance, 15th to 16th centuries, with its revival of art and learning. We applaud the rise of the Cartesian and Newtonian world systems in the 17th century. We applaud the Age of Reason, the Enlightenment of the 18th century, with its conviction in the power of human reason. We applaud the Age of Science, 17th to 20th centuries. And we too easily forget the growing dismay of ordinary men and women in a universe that, century by century, progressively became more meaningless and senseless. With the decline and death of the old universes, anthropomorphic and anthropocentric, humanity was cast aimlessly adrift in an alien universe. Furthermore, we believe that the universe is not created in the image of human beings. It is not a magic realm alive with human-like spirits. We are not the central fief, and gods and goddesses do not rule the universe. It is not anthropomorphic. Rather, as Pythagoras saw, we measure the universe. Hence, the cosmos is anthropometric. Let us try to grasp this idea. We have minds, or as some would say, we have brains. For our purpose, it is unnecessary to inquire into the nature of the mind-brain and attempt to probe its mysteries. Whether we consider the mind a non-physical entity of psychic activity or a physical brain engaged in bioelectrochemical processes, it remains irrelevant to our purpose. We have minds into which information pours via the sensory pathways, and from this information we devise in our mind brains, the Aristotelian, Stoic, Epicurean, Zoroastrian, Neoplatonic, medieval, Cartesian, Newtonian, and all the other universes that have dominated human thought in different ages. We observe plants and flower pots and other things, and devise grand theories that relate and explain them. And these theories reside not in the things themselves, but in our minds, brains. Different universes prevail at each step in the history of cosmology. And every university society is a grand mental edifice that makes sense of the human experience. Each anthropomorphic universe consists of ideas devised by human beings seeking to understand what they observe and experience. For those lost in the vast and apparently meaningless modern universe, there is comfort in the realization that all universes are anthropometric. Men and women created and measured the medieval universe, a fact that the medievalists themselves would have vehemently denied. The modern university, which resets its bioelectric chemical brains to ponder over it, is also human-made. Like the medieval universe, other universes will inevitably replace it as time passes. The future universes will almost certainly differ from our modern version. Nevertheless, they will all be anthropocentric, because man is the measure of all things. Of course, the universe is not human-made, but we have no true conception. All we know is that it contains us, the dreamers of universes. Cosmology and civilization are intimately entwined. Every institution has a past that shapes the course of its society. Where there is a society, there is a universe. Where there is a universe, there is a society of thought. This intimate relationship is most evident in primitive cosmology, where mythology and society mirror each other, and the ways of gods and goddesses are the ways of men and women. Cruel people create cruel gods who sanction cruel behavior, and peaceful people create peaceful gods who foster peaceful behavior. The interplay between cosmology and society in the modern world is as strong as ever, if not stronger, but often in less easily recognized forms. Plenitude, which dates back to Plato, has had an amazing influence since the 15th century. The most potent and in-flight ideas in any society are, without a doubt, those linked to the university. These ideas shape histories, inspire civilizations, foment wars, build kingdoms, launch empires, and create political systems. The principle of plenitude originated in the anthropocentric belief that the universe was created for humanity by an intelligible supreme being. In its simplest form, it states that a beneficent creator has given humans an earth of unlimited bounty for their use. The formal argument is presented below. The supreme being is without limitation, because limitation implies imperfection, which is contrary to belief. The unlimited potential of the supreme being manifests in the created world's unlimited actuality. The earth necessarily displays every form of reality in inexhaustible abundance. This is the principle of plenitude that saturates Western culture. Europeans developed the principle of plenitude, were guided by it, and have since exported it all around the world. Telescopes revealed the abundance of the heavens. Microscopes revealed a teeming world of microorganisms, and mariners' worldwide voyages opened dazzling vistas of a vast and bountiful earth. The principle of plenitude shaped political ideologies. The principle guaranteed endless untapped wealth, and free enterprise flourished as never before. To counteract depletion and prevent population growth, pushing further east and west towards the enticing rewards of untouched lands was necessary. "The real price of anything is the toil and trouble of acquiring it," said Adam Smith. "Go east. The streets are paved in gold. Go west. Beyond the sunset lie lands of unharvested wealth." Husbandry of finite resources was not part of plenitude philosophy. People confidently believed that everything existed in unlimited abundance, and when anything became exhausted, such as the elimination of the bison herds, the extinction of the carrier pigeons and the great ox, they were taken by surprise and felt cheated. One response came from Karl Marx's message. "In the Communist Manifesto, we are told the less wealthy have nothing to lose but their chains. They have a world to win." Sadly, the principle of plenitude, which now lies buried deep in our cultural legacy and has been distributed in many forms worldwide, is only a unchecked population increase, fast resource depletion, and environmental and atmospheric pollution define our era of crises. And we find great fascination in predictions of doom. Our daily thoughts still revolve around old concepts of cosmological breadth, many of which are entirely inappropriate in modern society. We seem caught in the misguiding logic of out-of-date academic ideas threatening to wipe us off. More than any other event, this one brought about the Industrial Revolution, which has transformed our way of life. Many claim that the Industrial Revolution directly caused today's problems. But the ideas, the belief systems, that direct the use of technology are the ones to blame, not the technologies. Let's say space visitors come upon a planet ruined by unrestrained technology and die. Space travelers cannot automatically conclude from their studies that technology was responsible for the destruction. They have to look for proof, suggesting the nature of the beliefs of the disappeared people. How did the beliefs of the people affect their destroyed planet? Their studies will likely lead them to conclude that ancient cosmology, based on ideas the people had rejected and yet driven to their doom, is the cause of the ruined world. One can consider the term universe to combine diversity and unity. The harmonic whole of all reality is indicated by the word cosmos. Still, what precisely defines unity, diversity, harmony, and reality? Cosmology has two separate languages. The first speaks of universes, and the second of cosmologies. Cosmology is the study of many worlds in the first sense. Each universe is a model of the others. Usually, cosmological study concentrates on the universe as it is known in the present age. Second, several cosmologies study the universe. Every cosmology is unique to a particular society. One cosmology investigates many worlds, or another investigates a single universe. The first speaks often of worlds, and the second of the universe. In this podcast, we follow the first approach since it avoids using the word universe, except occasionally, to clarify a point, and does not promote the illusion that the universe is a known or even knowable thing. Homo sapiens first emerged some 1 million years ago. Viewed by the early humans, how did the surroundings reflect? In his book on the Tobriand Islanders of Melanesia, Bronislaw Malinowski wrote, "I shall invite my readers to step outside the closed study of the theorist into the open air of the logical field." Using his observations and many other anthropologists researching various societies, we discover sophisticated and straightforward cultures and complex languages. Most likely, nowhere in today's world do truly primitive human beings provide us with an understanding of how our distant ancestors thought and lived. In his book, Primitive Culture, Victorian anthropologist Edward Tyler claimed that the world of prehistoric people was possessed, pervaded, and crowded with spiritual beings. He developed the animist theory. Early humans projected their feelings and intentions into the environment, and the world could almost always explain anything that required explanation. With the expansion in language and abstract thought, the ambient spirits combined to form strong nature spirits, godlings, gods, and goddesses over time. Assuming as a basic premise that religion was born with the rise of the gods, James Frazer wrote in The Golden Bough that the idea of gods as superhuman beings with powers far beyond anything humans possess has slowly evolved throughout history. Frazer examined the change of animism into theism and the transfer of control over the gigantic machinery of nature to the gods. Generally speaking, religion is not easily defined. It comprises ideas and emotions. While the religious ideas that inspire people are unique to every society, the religious emotions individuals feel are the same in all civilizations. Religious emotions are most likely natural human feelings and necessary for the survival of human civilizations. Faith is the conviction in the absolute truth of religious ideas. Theology studies those ideas. Ideas always have cosmological significance. People in many cultures have experienced similar religious emotions throughout history, yet they have held quite different religious beliefs, each regarded absolutely true by its followers. Understanding the universality of religious emotions and the variety of religious beliefs implies that Frazer was mistaken in following the birth of gods as the source of religion. Possibly religion is as old as Homo sapiens. It is rather typical to mistake religious ideas for religious emotions. Members of religious institutions who insist on holding their mythic beliefs unintentionally confuse theory with emotional experience and believe they cannot have religion without primitive cosmology. They overlook that rejecting mythic cosmology does not lead science to conflict with religious experience. For example, the modern view of light as a quantum of energy has not deprived us of the sensation of color and the emotional experience accompanying it. Mythology studies ideas and narratives that provide a historical understanding of the belief systems of other, usually earlier, societies. Though they are credible in the belief systems in which they first arose, myths become amazing when adopted into other civilizations' belief systems. Good and evil are much influenced by cosmological ideas. About 500,000 men, women, and children admitted heresy and witchcraft under torture and were burned to death in the witch universe of the late Middle Ages, known as the Renaissance, and of the Age of Reason, known as the Enlightenment. Heretics were supposed to burn permanently in hell, and their temporary suffering on earth was justified if they were rescued from the constant fire of hell. Cruel people create cruel gods who sanction cruel behavior, says the maxim. Their numbers multiplied and seemed limitless. And the terrible fact was that whenever you found one witch and used the just and proper instruments of inquiry, you inevitably found many others. Still multiplied are male and female witches who are evilly consumed by fire. It seems that these horrible creatures rule all Christianity. Previously unheard of nations are now swarming around us. The more we search, the more we discover. All modern viewers agree they have acquired powers hitherto unheard of. A sophisticated international organization and social habits of amazing grace. Some of the most influential brains of the day move from human sciences to investigate this recently discovered continent, this America of the spiritual world. Other research workers, experimenters in confessional and torture chambers, theorists in libraries and cloisters, leave the facts more securely established and the prospect even more frightening constantly and amply confits the details they discovered. Instead of going toward extinction, the witches exploded in numbers, apparently ready to overwhelm Christendom with the might of triumphant evil. Considered by the popes as bewitchment and the outcome of working with devils, protesting in any form against witch hunting as inhuman in a time of emergency was pure lunacy. Published posthumously in 1952, Edward Milne's last work, Modern Cosmology and the Christian Idea of God, notes, "There is a remarkable difference between physics and philosophy. Although physicists generally agree at any moment, the physical theories of any decade differ significantly from those of each one following decade, at least in the 20th century. Though they disagree, the major philosophical problems never change with time. The man of science should be basically a rebel, a prophet rather than a priest, who should not be embarrassed by discovering himself in challenge to authority. Usually holding that science and religion have no direct influence on one another, the hard-baked or hard-boiled scientist often uses nodding words. On the other hand, one cannot study cosmology without a religious perspective toward the world. Presuming the rationality of the universe can give no rationale for it short of a rational creator. While philosophers and theologians have an emotional commitment to their ideas that they believe in them, scientists see their theories and concepts differently. Scientists are interested in generating several theoretically coherent solutions. Hence, any evaluation of their truth depends on observations. It does not bother scientists to propose several mutually exclusive hypotheses for the same event. Says Herbert Butterfield in The Origins of Modern Science, outshines everything since the rise of Christianity and reduces the Renaissance and Reformation to the rank of mere episodes, and looms so large as the real origin both of the modern world and the modern mentality that our customary periodizing of European history has become an anachronism and an encumbrance. Butterfield argues that science saved Europe from the crazed witch universe. The Renaissance's witch frenzy cannot be quelled by the arts, religion, or sciences. Science separated the supernatural from the natural, reaching a new universe more fit for defining the boundaries of human impact over nature. Perhaps the world of external facts is much more fertile and plastic than we have ventured to suppose. It may be that all these cosmologies and many more analyses and classifications are genuine ways of arranging what nature offers to our understanding, and that the main condition determining our selection between them is something in us rather than something in the external world. Natural science describes nature as exposed to our method of questioning. It is part of the interaction between nature and ourselves. It does not only describe and explain nature. The old masters do not take any model nearly so seriously as the rest of us. C.S. Lewis notes in The Discarded Image. Later, he says, "An unprovoked assault of new facts, as unprovoked as the Nova of 1572, may violently destroy our model. But I think it's more likely to change when broad mental temperamental changes in our descendants demand it. We won't build the new model without evidence. It will manifest itself when the inner drive for it gains sufficient force. That will be factual evidence. Still, nature provides most of her evidence in reply to our questions. The great chain first motivated the missing links concept long before Darwin. In Arthur Lovejoy's The Great Chain of Being, we read, next to the word nature, the sacred phrase of the 18th century, playing a somewhat analogous role to that of the blessed word evolution. Lovejoy claimed that the great chain of being was closely related to the concept of plenitude. Not so long ago, people thought the planet was virtually inexhaustible in its capacity to meet human needs and as a sink for human waste products. Those who wanted to leave tired farms or the mess of city life could always find a clean, unspoiled setting. Rich lodes, frontiers, virgin woods, and sizable blank areas on the map, waiting to be explored, where as far as I know it has never been distinguished by a suitable term. For want of this, its identification in different contexts and in different phrasings seems to have escaped notice by historians. I will call it the plenitude principle. In The Tragedy of the Commons, Garrett Hardin explores how historical mythologies and cosmological ideas shape our lives. Believing ownership is a natural and divine right, people try to maximize their share of a common resource. Every herder wants to grow his herd. Hence, he grazes his animals on shared territory. By restricting the number of people and animals below the capacity of the land, disease and tribal warfare preserve a balance. Then comes a more civilized and orderly way of life that, with less violence and disease, loads more on the commons. All herders believe that if I expand my herd, the loss resulting from overgrazing will be shared by all, and my gain will surpass my loss. This is the tragedy. Every person, says Hardin, is trapped into a system that pushes him to raise his herd without limit, in a restricted planet. Sadly, most problems arising from out-of-date cosmic myths, such as the great chain of being, the principle of plenitude, and the capacity to reproduce without limit, do not have technological solutions. The place all people rush to is ruined. Most people who agonize about the population issue are fair to remark that farming the oceans or developing new wheat strains will technically address the issue. My thesis is that the population problem, as conventionally understood, is a member of the class of human issues known as technical solution problems. A technical solution may be defined as one that requires a change only in the techniques of the natural sciences, demands little or nothing in the way of change in human values, or ideas of morality. Correctly speaking, astrolatry is the worship of stars. Astromancy is the practice of soothsaying and divination using celestial configurations. We call the study of living things biology. Correctly speaking, astrology evolved and replaced astrolatry and astromancy in corruption. Nowadays, astrology reflects the mythological conviction that human behavior is influenced by celestial bodies. Millions of Americans read the astrological, or rather astromancy, articles in daily newspapers. They find astromancy fascinating and entertaining, since it is anthropocentric and links human beings and the universe in ways most people find relevant. Some people treat it seriously, then by modern standards it becomes absurd. Most people, however, find it interesting since it plays to vestigial aspects of our cultural background. In Objections to Astrology, Bart Bok, Lawrence Jerome, and 19 other eminent scientists convey their dismay at the growing acceptance of astrology in many spheres of life. Those who still believe in astrology do so despite the paucity of solid scientific data against it. Nature is a dull air, boundless, scentless, colourless. Mere the hurrying of material, endlessly, meaninglessly, Alfred Whitehead says in Science and the Modern World. Could many people find themselves in a meaningless reality where their religions and ideas have disappeared? How can we handle this negative situation in which people find comfort in the astronomy that science seeks to eradicate? Sunday schools did not arrest the flight from religion. Would additional introductory science courses arrest the flight from the scientific universe? Examining Adam Smith's well-known comment, "The real price of anything is the toil and trouble of acquiring it," requires some thought. We should consider how our activities affect the environment over the long run. These results could show that those who inherit the later depletion and dispersion bear the actual cost. Have we already started to observe the exact price? List issues without a technical response here. While new drugs treat old diseases, they also aggravate population increase problems and might cause more suffering. In Hardin's view, population increase calls for either a change in values or moral principles, as it is a problem without a technical answer. Would occupying space help to address population issues? With the increase in birth rate, Sebastian von Herner in Population Explosion and Interstellar Expansion demonstrates in at least 500 years that such an endeavor may solve the problem. Full of people, the human space bubble would expand faster and faster and, in 500 years, at the speed of light. Every colonized planet would get more packed and deal with the same issues we have on Earth. To what degree is the West, with its concepts of plenitude, pharmacology, hygiene, and technology, responsible for the astonishing rise in human life and the decline in wildlife? All the labors of the ages, all the dedication, all the inspiration, all the noonday brightness of human genius are destined to be buried beneath. All the things, if not quite beyond dispute, are now so nearly sure that no philosophy which rejects them can hope to stand. Look at any problem closely enough. The same excitement, wonder, and mystery will return. More knowledge attracts one to discover more incredible secrets from farther depths. Surely it is a great adventure. We are never worried that the answer may prove disappointing. We turn over each fresh stone with delight and confidence to discover unimagined weirdness, which generates more beautiful questions and mysteries. Babylonian sky-gazers split the heavens into the zodiac's constellations, compiled star catalogues, and noted planetary motions 4,000 years ago. They developed rules of arithmetic, created multiplication tables, and were adept in computer arts. They foresaw eclipses and created calendars projecting the seasons and dates of the full and new moon by analyzing the rhythmic changes in the heavens. All of this was done as religious divination, astromancy, and astrolatry. Driven by mythic ideas, the Babylonian wizards plotted the heavens but neglected to create natural explanations of celestial motions. Greek philosopher-scientists aim to explain the world's complexity by lowering it to an interaction of elements from the time of Thales of Miletus, 6th century BC. Water, Thales, 6th century BC. Air, Anaximenes, 6th century BC. Seeds, Anaxagoras, 6th century BC. And atoms, Leucippus, 500 BC. Proposed elements or main constituents were Empedocles, described in the 5th century BC, Earth. Xenophanes, 5th century BC. Water, air, and ether. Heraclitus, 5th century BC. Aristotle characterized earth, water, air, ether, etc. in the 4th century BC. There exists an ultimate substance, said Thales, from which all things come to be. It is being conserved. Early scientists asked how things worked and used analogies from mechanical arts and crafts, such as pottery and metalwork. They believed in preserving elements that constantly combine and recombine to form objects of different shapes and colors. They rejected supernatural, mythological explanations of natural phenomena, reduced everything to basic elements, and used conservation rules. They freely hypothesized and made experiments based on hypotheses. All this is the essence of the scientific method. In the 6th century BC, starting with Pythagoras, Heraclitus, and Parmenides, we see the budding of novel and potent ideas. Pythagoras of Samos, who founded an influential school of advanced thought, and may have been the first to use the word philosopher, taught that the earth is a sphere and mathematical relations govern the harmonies of the cosmos. Heraclitus of Ephesus, known as the weeping philosopher because of his pessimism, said, "Everything changes, nothing endures, and the fundamental element is fire." He conceived a universe of tempestuous flux governed by a conflict of opposing forces and said wisdom consists of knowing how things change. Parmenides of Elea said, "Nothing changes, everything endures, and wisdom consists of rejecting sensory deceptions." He conceived an abstract universe of truth, beauty, and justice in which all change was an illusion of the senses. The ideas of Heraclitus about constant change and Parmenides about an unchanging reality are unique. The first predicts the Newtonian universe with its moving parts, while the second predicts the Riemannian spacetime found in relativity theory. Harmonies based on Pythagoras. Whereas the Hellenic, Greek, celestial observers were philosophers and scientists, the Babylonian astronomers were priests and prophets. The Babylonians excelled in arithmetic and abstraction, while the Greeks excelled in geometry and metaphor. Diogenes Laertius, 3rd century AD, reported that Pythagoras was the first to refer to the heavens, cosmos, and earth as spheres. Pythagoras visualized a universe of geometrical harmony and used spheres, circles, and vortical motions as basic forms in the universe's design. The Pythagoreans held that the celestial bodies were spheres whirling in perfect circles around a central cosmic fire invisible to humans. Melodic notes emanated from the heavenly bodies, and their celestial symphony, or harmony of the spheres, was beyond human hearing. Socrates, living in Athens, Socrates, about 470–399 BC, stressed the value of humanistic studies and taught the liberal arts. He corrected the path of philosophy using his pupil Plato. Almost nothing that has survived has been written by him. Plato's writings bear his teachings. Socrates thought the immortal soul, or mind, lived in a mortal house of clay. While the Greek scientists, using analogies from the mechanical arts, observed the significance of how things worked, he underlined the need for questions starting with why. What consequences does it follow if atoms help explain how matter is built? Indeed, the reason behind the atom's existence is more crucial than anything else. Only pure reason, looking within the soul, can ascertain their need and goal. At 70, he was charged with misleading his students with heretical ideas and condemned to death. Establishing the first advanced learning institution in Athens, Plato, about 427–347 BC, founded the academy. His lessons have been more in flux than any other philosophers over the ages. He combined the Pythagorean and Socratic ideas into a cosmology, stressing the significant difference between appearance and reality, between fugitive matter and concrete mind. The transitory fantastic world is just a shadow of the always real world. The source of order, coherence, and harmony is the mind, which controls the naturally disorganized, incoherent, and discordant matter. In the parable of the cave, Plato pictures people imprisoned in a cave, unable to move. Though they cannot see it, the light comes behind them and highlights the wall in front. Moving objects behind them creates shadows on the lit wall. They only see shadows on the wall and remain bound all their life. Surely, Plato said, such persons would believe the shadows to be the only realities. This parable holds that the intelligent mind can only reach the real world beyond the senses, and we are prisoners of our senses. Three cosmic systems of the ancient world: Epicureanism, Stoicism, Aristotelianism. From the 4th century BC to the 3rd century AD, three rational belief systems, Aristotelianism, Epicureanism, and Stoicism, dominated the Mediterranean world. Every universe fuses ethical, scientific, and philosophical ideas. Deep in the Western cultural legacy are remnants of all three worlds. Initially developed in Athens, the Aristotelian universe of celestial spheres was centuries later embraced by the Judaic, Christian, and Islamic worlds. Including theistic aspects from Babylonian and Zoroastrian faiths, it became the medieval universe that endured until the 16th century. Originating in the late 4th century, the Epicurean universe of endless worlds was highly popular among middle-class and educated people for centuries. Emphasizing the life sciences, it rejected the gods as explicative agents in the natural world, and embraced the equality of men and women using atomist principles. Later, everywhere, the Judaic, Christian, and Islamic worlds denounced it for its atheism. Founded in Athens in the 3rd century, the Stoic universe was well known throughout the Roman Empire. It had two sections: a finite universe of stars and a surrounding emptiness that went to inactivity. The Stoics underlined the need for the sciences as well as ethical values and responsibilities. Aristotelian universe. The universe of two spheres. The Pythagorean two-sphere universe was fashionable during Plato's lifetime at the Academy in Athens in the 4th century BC. It comprised an outer sphere, the stars, encircling a central sphere, the Earth. The planet slid in erratic paths between the two spheres. To all earnest students, Plato asked, what are the uniform and ordered movements of the planets? The numerous sphere universe. Student of Plato Eudoxus suggested that a central spherical Earth encircled by concentric and rotating spheres would help to depict the universe. As in the Pythagorean two-sphere model, Eudoxus's idea had the outermost sphere rotating daily and supporting the stars. Intermediate spheres also supported the planets and spun about differently inclined axes. At first, these genome trial devices sought to be simple analogies to a modern planetarium's mechanical and optical elements. Aristotle turned the analogy, though, into a helpful tool. Aristotle, 384–322 BC, was born in Macedonia and enrolled at Plato's Academy. Aristotle taught while strolling about with his students, so he established his lyceum, the peripatetic school. His lecture notes filled 150 volumes. His interests were universal. He was a meticulous observer, and the life sciences piqued his central curiosity. He spoke on the great chain of life and the development of different forms. Aristotle feared accusations of impiety against the gods, and fled Athens so that Athens should not sin twice against philosophy when his pupil and later patron, Alexander the Great, passed away. Aristotle adopted the many-sphere model and invested the spheres with physical and etheric reality. The planets Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn are attached to the transparent spheres whirling around the Earth. The planetary and star motions called for up to 56 supporting spheres. The Earth and the inner sublunar sphere were composed of the terrestrial elements of water, air, and fire. A fifth element, known as ether, later known as quintessence, comprised the outer celestial spheres. Whereas the natural motion of the ether was endless revolution around the Earth, the terrestrial elements sought their proper places according to weight by up and down. Aristotle's universe holds that all motion calls for constant force application. Direct touch with other bodies drives and pulls them, guiding their movement. Aristotle maintained that isolated bodies would be motionless, so the void, or vacuum, could not exist. Interatomic voids, therefore, prevented the existence of atoms, the smallest matter particles. Moreover, if atoms existed, as claimed by the atomist thinkers, then no force could have direct contact, and all bodies would be always motionless. Aristotle claimed that since the Aristotelian universe's outer boundary revolved around Earth, the whole universe formed a cosmic sphere of limited size, necessarily finite. Straight lines could not be inbounding length, since they would extend beyond the universe. If the heavens are infinite and revolve in a circle, they will traverse an infinite distance, finite time. This we know is impossible. Consequently, whereas circles were complete and flawless, all straight lines were incomplete and flawed. The Earth did not rotate, since the terrestrial components of the perishable form should have imperfect vertical motion toward and away from the cosmic center. Furthermore fitting was that the etheric element building the celestial spheres should have just perfect circular motion. Therefore, it makes sense for the heavens to move ceaseless. Aristotle's system was a spatially finite universe, in a steady state. It had existed unchanged through eternity, and its perfect motions had no beginning or end. Everything ceases to move when it comes to its natural destination. The rotating spheres of Eudoxus did not explain planetary retrogression satisfactorily, and failed to explain why planets have increased brightness during their periods of retrograde motion. A step in solving this problem was the idea of eccentric circles. The Earth remained at the center of the universe, but each celestial circle had its center displaced by a certain amount from the Earth. Another important step taken in the 3rd century BC was the introduction of epicycles. The epicycles were additional circular motions, explaining why the planets moved backward, retrogression, and forward, progression, across the sky, and were brighter during backward motion. Ptolemies. Claudius Ptolemy, actual dates unknown, an astronomer and mathematician at the Museum of Alexandria in the 2nd century AD, did for astronomy what Euclid, also at the museum 4 centuries previously, had done for geometry. He brought together many of the ideas and observations made in previous centuries. In his principal work, Almagest, the Great System in Arabic, he used eccentrics, epicycles, and equants. The equant, or equalizing point, is an off-center point where the epicycle moves at a uniform angular rate. By combining eccentrics, epicycles, and equants, along with careful calculations, it became possible to accurately mimic the movements of the planets in a universe where Earth is at the center. The result was a geometric marvel. It endured for 1400 years until the revolutionary works of Copernicus, Kepler, and Galileo overthrew it. Ptolemy's presentation of the final form of the Aristotelian universe rejected the idea of atoms, the Democritian suggestion that the Milky Way is an agglomeration of stars, Heraclides' suggestion that the Earth rotates daily, and Aristarchus' theory, approved by Archimedes, that the Earth rotates daily and revolves annually about the Sun. The Epicurean universe. Atomic beginnings. Parmenides' focus on the one's unity was opposed by philosophers who stressed the many's plurality. The idea of a void, in which numberless discrete entities moved, opposed the idea of a changeless, undifferentiated continuum. Anaxagoras demonstrated this concept in the 6th century BC. H. They said the universe was infinite in extent and contained an endless number of small seeds. These seeds, later called atoms, indivisible, had properties that impacted our senses, enabling us to perceive the world of matter. A universal rational mind, not God's, ruled the universe, and the same substances comprised the heavens and the earth. Anaxagoras faced accusations of impiety and underwent a trial for heresy. Powerful friends defended him, and although acquitted, he fled the hostility of Athens. Leucippus 5th century BC, of Miletus, of whom very little is known, is credited with the invention of the atomic theory. He was the first to state clearly the principle of causality. All events are the effects of preceding causes. Everything happens out of reason and necessity. Democritus of Abdera, a student of Leucippus, said, "Nothing can be created out of nothing, nor can it be destroyed and returned to nothing." Leucippus's atomist theory, elaborated by Democritus, was not accepted by the Athenian philosophers Socrates, Plato, and Aristotle, and we are indebted to the later teachings of the Epicureans for keeping the atomist's ideas alive. The original atomist universe consisted of only atoms and the void. The atoms were infinite in number, and the void was infinite in extent. Atoms were made of the same substance, but differed in shape and size. They moved freely through the void, forever colliding and aggregating to form moons, planets, and stars, which slowly dissolved back into atoms. Epicurus, 341–270 BC, of Samos, settled in Athens and founded the Epicurean school of philosophy, the first school to admit women students. The Epicureans adopted the atomist theory of numberless worlds formed by the aggregations of atoms. Epicureans believed that the human being is an evolved and superior animal, that the gods exist in ourselves and not the external world, and that the greatest pleasures stem from moderate and mutually supportive living. Their philosophy, based on atomist principles, flourished widely for 600 years in the Greco-Roman world among thoughtful people, and perished with the spread of Judaism, Christianity, and Islam. Bear this well in mind, Roman poet Lucretius says in the 1st century BC in his epic poem, that nature is free and controlled by proud masters and runs the universe without the aid of gods. Epicureanism is praised like the universe. Who can exclude the measureless total sum? Who can have in forceful hands the incredible power of the incomprehensible? Who can spin all the firmaments together and foment with the etheric forces all the productive earth? Who can be everywhere, at all times? The answer was only nature itself. Religious institutions responding to Epicureanism wherever possible, and making the gods even more remote and powerful. A surviving manuscript of the Lucretian poem was found in 1417 in an Eastern European monastery, and soon after became widely known by the invention of printing. Its effect, little recorded by historians, was perhaps greater than the work of Copernicus. The Stoic universe. Zeno of Citium. Zeno of Citium, born about 334 and died about 262 BC, founded the popular Stoic school of philosophy in Athens. He lectured in a roofed colonnade called a stoa, and his philosophy, known as Stoicism, appealed to all classes, from enslaved people to aristocrats. He exalted the ethical principles of duty and justice. We may imagine him calling to those strolling by, "Have fortitude in the face of adversity, for fate rules the world. Weep not, you are powerful, and the divine spirit throbs on earth and in the heavens, swelling and subsiding from age to age, from cycle to cycle on the wheel of time. The gods exist in high places, in nature and in ourselves. Look at it all, but be not amazed. The soul has seen it many times before." Stoic ethical values and codes of behavior, modeled in the writings of Seneca and Marcus Aurelius, now permeate Western culture. Stoicism in the 1st century BC was far more popular than Epicureanism, particularly among the Romans. The Stoics believed in fate, that all was predestined, and that the mind manifested through the gods and mortals as divine spirits governed the universe. They thought the stars were alive and the universe was a living, organic whole. The Earth was also a living entity. The Stoics believed that the starry cosmos was finite, and beyond the finite cosmos stretched a mysterious void. Some Stoic schools believe must slowly pulsated in size and periodically passed through catastrophic upheavals. 2,000 years later, the Stoic universe, a finite starry cosmos in an infinite void, formed the basis of the 19th century Victorian universe. Religions of the mystery. Science, which analyzes and classifies, began in the Mediterranean in the 6th century BC. At the same time, intellectual activity quickened elsewhere in many lands. The teachings of Zoroaster, or Zarathustra, in Persia, Iran, Gautama the Buddha, and Mahavira the Jain in India, and Confucius and Lao Tzu in China gave birth to ethical religious movements. Religious doctrine led to the formulation of moral codes of civil behavior, which were previously unrelated to religion. The spread of these enlightened teachings created an abhorrence of human sacrifice that was previously a worldwide religious practice. Zoroaster in Persia was the first prophet to teach a doctrine of rewards and punishments in the afterlife. His belief in one God, Ahura Mazda, who rules the universe with light, and the idea that good people go to heaven while bad people go to hell, was accepted by the Medes and Persians, with added beliefs about angels and demons, and influenced the later religions of Mithraism and Manichaeism. The medieval universe. Greek science flourished for 700 years, from the 6th century BC to the 2nd century AD, from Thales of Ionia to Ptolemy of Alexandria. By the end of the 2nd century AD, however, the blaze of Greek inspiration had died to a weak glow. Early Middle Ages. With the fall of the Roman Empire in the 5th century, cultural darkness descended on Europe and all intellectual pursuits languished under the rule of barbarians. In the ensuing Dark Ages, the early Middle Ages, the universe reverted to a mythic polarization of heaven and hell, with the earth as a rectangular tabernacle surrounded by an abyss of water. A few scholars, such as Boethius and the Venerable Bede, were aware of Greek learning through the Latin commentaries of Cicero, Pliny, and others. Despite the decline of European learning, Byzantium, Syria, and Persia managed to preserve remnants of ancient knowledge. Arabs spilled from their deserts in the 7th century to establish a vast Islamic empire spanning the Atlantic to India. Libraries of ancient, lost manuscripts were gathered, and academics moved to Damascus, Baghdad, Cordoba, and other centers of the new civilization. The crafts, arts, and sciences once more flourished. Translated into Syriac, Arabic, Greek, Egyptian, Persian, Chinese, and Indian literature, was combined into copious commentary. The new learning permeated the known globe, including China and Europe. Scholars in the Islamic world confirmed the Earth's spherical form and geocentric universe model by the 9th century. The Islamic Empire has helped us all preserve and share ancient knowledge, awakening Europe. Sadly, the 14th century Mongolian and Turkic invasions destroyed the traditional Islamic and Chinese cultures. The Middle Ages in the high level. Exciting knowledge from Arab lands cut across the early Middle Ages gloom. New concepts, such as realizing they are essential to grasp, change established wisdom. In the 11th century, Canterbury's Archbishop, Anselm, first proposed the Empyrean, a sphere of purest fire where God lived outside the domain of stars. From Arabic, and then straight from the original Greek, many hard-working intellectuals translated the writings of Plato, Aristotle, Euclid, Galen, and other philosophers, mathematicians, and scientists of the ancient world into medieval Latin. Communities of translators and educated scholars established the universities. The new knowledge surpassed the boundaries of the monastery and cathedral schools. Early in the 13th century, Thomas Aquinas demonstrated how minor modinials could allow Christian doctrine to fit in the Aristotelian universe. Humans kept their immortality. The universe lost its eternity. The 14th century brought the finest form for the following medieval universe. It was a grand unification of the material and spiritual worlds, blessed by religion, approved by philosophy, and rationalized by geocentric science. However, in the 13th century's reawakened Europe, Ptolemy's astronomy and Aristotle's physics were much sought after. According to Franciscan monk Roger Bacon, the scientific approach was based on observations rather than reading ancient texts, applying mathematics, and verifying calculations using tests. Christian doctrine, threatened by the wholesale acceptance of Aristotelian knowledge, alarmed ecclesiastical authorities. Although they agreed that the Earth is a sphere at the center of the universe, they refuted the Aristotelian case that God could not move if he willed or create other worlds if he willed, declaring the 219 condemnations in 1277. Paris's bishop Étienne Tempier rejected the Aristotelian limitations on God's power. Said the bishop, "God's power is unbounded. He is everywhere and cannot be confined to any one place." In cosmology, the condemnations are a landmark event. The explosive concept of an all-powerful God destroyed the boundaries of the Aristotelian universe. The new universe had to be able to house an unbounded God. To this end, Bradwardine expanded Anselm's Empyrean into an infinite extra-mundane void. Thomas Bradwardine of Oxford, who became Archbishop of Canterbury, said, "God is that whose power is not numbered and whose being is not enclosed." Empedocles of the 5th century BC had written, "God is that whose power is not numbered and whose being is not enclosed." Beyond the domain of stars lay an enigmatic, unbounded world inhabited by God. He made the limited Aristotelian universe unboundedly stoic. Nicolas Oresme, also in France in the 14th century, said, "Motion can be perceived only when one body alters its position relative to another." He refuted old arguments claiming that the Earth could not rotate, and pointed out that Heraclides' theory of a rotating Earth greatly simplified the structure of the heavens. The exciting idea of an infinite universe introduced by the discovery of the poem The Nature of the Universe surely affected the ideas of many intellectuals in the 15th century. Cardinal Nicholas of Cusa maintained that the universe must also be without an edge and center, since God created it, boundless and without location. The created universe reflected the qualities of the Creator since, in his treatise of learned ignorance, he made the well-known remark that the universe is a sphere of which the center is everywhere, and the circumference nowhere. Though nothing in reality drives us to see the Earth as the center of the universe, said Nicholas of Cusa, it is convenient. An actual center does not exist. Thus he could not find any justification for the Earth not moving. The heliocentric university system. Beginning among the Pythagoreans, the Copernican revolution concluded with the Cartesians and Newtonians. Copernicus and Aristarchus stood among its heroes. The revolution started. It helped them escape their geocentric fixation and cleared the path for the final collapse of the anthropocentric universe. Copernicus. A canon of the Catholic Church, Nicolaus Copernicus, 1473 to 1543, showed the viability of a heliocentric universe in the 16th century. While studying the Ptolemaic system as a student in Italy, he was horrified by its abdication of the Platonic ideal of perfect circular motion. Aristotle had embraced this ideal, but Ptolemy dropped it when he brought equants. Copernicus also knew the heliocentric theory Aristarchus had proposed. This view holds that the Earth revolves around the Sun. Hence, the other planets seem forward and backward across the sky. Copernicus thought that equants could be eliminated from a heliocentric system, restoring the original idea of perfect circular motion. He committed his life to computing and building heliocentric orbits. Complementing the Almagest in scope, Copernicus's massive work, Revolutions of the Celestial Spheres, went into print in 1543, just before his death. In an earlier work, he wrote, "All orbs revolve about the Sun, taken as their center point, and so the Sun is the center of the universe." In the Revolutions of the Celestial Spheres, he wrote, "Why then do we hesitate to allow the Earth the natural mobility of its spherical shape, instead of proposing that the whole universe, and whose boundaries are unknown and unknowable, is in rotation. The arguments he used to justify the Earth's rotation were similar to those proposed in the previous century by Oresme. From a rotating Earth, it was a straightforward step to a moving Earth. We thus assert that the center of the Earth, carrying the Moon's orbit, passes in a great orbit among the other planets in an annual revolution around the Sun. That near the Sun is the center of the universe, and that whereas the Sun is at rest, any apparent motion of the Sun can be better explained by the motion of the Earth. Sadly, most astronomers were skeptical at first, since the Copernican dream of a simpler universe did not materialize. Copernicus's labor to bring the heliocentric system into line with observations determined the necessary number of circles more or less directly. He needed more circles than ever before, and was still unable to match the accuracy attained by Ptolemy by searching equants. The University Infinite. Digges, Thomas. Born when Copernicus passed away was the astronomer and mathematician Thomas Digges, 1543–1595. In a perfect description of the celestial orbs, 1576, he went into great detail on the Copernican system. He presented a significant modi action, spreading the star sphere over unbounded space. Only 33 years after the publication of the Revolutions of the Celestial Spheres, and exactly 200 years before the Industrial Revolution and American Declaration of Independence, the universe had its sphere of stars ripped away. This orb of stairs, wrote Digges, xed infinitely up, extendeth itself in altitude spherically. Over several editions in the late 16th century, the perfect description encouraged ideas that changed the physical world. Bruno Giordano. A monk, Giordano Bruno, lived in London when Digges's book became well known. Emphasizing the logical conclusion, previously made by Nicholas of Cusa and others, that the universe must also be centerless. That in the universe, no center and circumference exist, but the center is everywhere. He previously embraced the idea of an edgeless universe. Bruno presented a Christianized version of the Epicurean universe, known from the poem by Lucretius, in his writings and travels. A universe of limited scope populated with innumerable planetary systems bursting with life. Bruno was the Copernican revolution's revolutionary champion. Thus is the excellence of God magnified, and the greatness of his kingdom made manifest. He is glorified not in one, but in countless suns, not in a single earth, but in 1,000, I say, in an inunity of worlds. Spending his last 7 years in an ecclesiastical prison, tormented and tormented, he refused to recant, and was burnt at the Rome stake in 1600. Tycho Brahe. Danish nobleman Tycho Brahe, 1546–1601, saw the planets with the best accuracy before developing telescopes. He turned away the Copernican paradigm for a basic reason. According to him, the stars would be seen in somewhat different directions at differing end times of the year if the Earth spun in a large circle around the Sun once annually. His observations failed to find this angular variation. Parallax. Should we drive the stars to such great distances where parallax loses measurement capability? He maintained that the stars are not just points of light without any dimensions. They have a particular size as seen by the unaided eye. Stars would have to be far bigger than the Sun if parallax were zero to look as they do. These days we understand that stars' apparent size, caused by diffraction, is misleading, and that they are even farther apart than Tycho could have imagined. Compromise. The Earth is stationary in the Tychonic system, and the Sun circles it. All the planets circle the Sun. Though it was called and still calls itself the Holy Roman Empire, was neither holy nor Roman, nor an empire in any way. Imaginative scientist Johannes Kepler, 1571–1630, overcame ill health, and became the imperial mathematician of the Holy Roman Empire, an agglomeration in Voltaire terms. He rejected the extreme proposition of a finite and centerless universe, and embraced the simple Copernican system with the sun at its center and the sphere of fixed stars at its outer edge. Published in 1606, this very cogitation carries with it, I don't know what secret hidden horror. Indeed, one finds oneself wandering in this massive city, to which are denied limits and centers, as well as all determinate places. In Cosmographical Mysteries, the first book, published in 1596, Kepler sought to untangle the universe's secrets. This work's germinal ideas developed in Kepler's later studies. The former imperial mathematician, it was Tycho Brahe. For years, Kepler battled to explain the motions of the planets, especially that of Mars, after inheriting Tycho's meticulous and exact observations of them. At last, he triumphed and released astronomy from the epicyclic motion model. His three fundamental rules of elliptical planetary motion were the basis stones of the Newtonian world system. Galileo, born the same year Shakespeare was born, Galileo Galilei, 1564–1642, passed death in the year Newton's birth. He made a significant contribution to astronomy by introducing the telescope. Through his telescope, Galileo observed something different from Ptolemaic doctrine. His theories ran counter to the Aristotelian view that the celestial sphere is the residence of spirits, declaring in his direct approach that the sublunar and heavenly worlds are physically similar. From the vantage point of the observing eye and critical mind, the Earth turns daily along an axis and revolves yearly around the sun. Galileo thought in Copernican fashion, though he showed no interest in Kepler's ideas. His astronomical findings, published in 1610 in the Starry Messenger, included mountains on the surface of the Moon, Jupiter's satellites, and many hitherto unresolved Milky Way stars. He addressed Tycho's criticism of the Copernican model. Galileo argued rightly that stars' apparent size is misleading even if his telescope magnified 30 times. Stars stayed the same apparent size as seen with the unaided eye. Galileo's most hostile rivals were academics and priests deeply immersed in Aristotle's writings. In the two great systems of the world, he criticized Aristotle's physics and Ptolemy's astronomy, contrasting the geocentric and heliocentric systems. Under the threat of torture, he recanted and abjured the heliocentric system. His views brought him into conflict with ecclesiastical authorities in old age. In geometry and music, the harmonic mean is quite significant. The 8 corners of a cube are the harmonic mean of their 6 faces and 12 edges. The Pythagoreans demonstrated, but the Babylonians found, the geometric algebraic rule. The square of the diagonal length of a right triangle equals the sum of the squares of its sides. Hence, among the magnitudes of the sides and diagonals of 2 right triangles, 3, 4, 5, 5, 12, 13, are instances. Generally incommensurable, Pythagoreans found that integral or fractional numbers cannot represent the sides and diagonal. The Greek philosopher Zeno of Elea, active in southern Italy in the 4th century BC, refuted the idea that the senses could reach the truth. The actual world is absolute and timeless. The world that one perceives is false and fleeting. His paradoxes, which aimed to refute the likelihood of change as seen by the senses, made him most famous. The most often cited paradox is the race Achilles runs against the tortoise. Assume Achilles runs 100 times faster than the tortoise and has a 100-meter start. Achilles runs 100 meters. The tortoise moves 1 meter. Achilles runs 1 meter. The tortoise moves 1 centimeter, and so on, in an inline number of declining steps. Achilles thus approaches ever more closely but never passes the tortoise. One could contend that the paradox is fallacious, since Achilles passes the tortoise as seen by the senses, and the inline number of steps spans only a finite interval. Philosophers still argue the paradox. The question is whether space and time are rightfully continuous and infinitely divided. But multitudinous atoms, swept along in multitudinous courses through infinite time by mutual clashes and their weight, have come together in every possible way and realized everything their combinations could form. So it comes about that a voyage of great duration, in which they have experienced every movement and conjunction, has finally brought together those whose sudden encounter normally forms the starting point of substantial fabrics: earth and sea and sky, and the races of life. Lucretius, the nature of the universe. Aristotle made secular the universal ideas: truth, beauty, justice, perfection, etc. Plato had created the divine, which imposed form on the disorganized world and associated them inseparably with material objects. In mythology, the gods dominated. In Plato's universe, the mind dominated. And in Aristotle's universe, the forms dominated. Aristotle somewhat restored the spirits of the age of magic, but with a difference. The spirits were now the natural forces and inherent qualities of matter. They still exist, masquerading as forces, masses, momenta, energies, potentials, wave functions, and so forth. In their new form, they had become the souls of material objects. Once more, humans live in a magical universe. The erratic spirits are now the disciplined dancers in a ballet of weaving forces and waves. 5 Jewish people came across Zoroastrianism with its division of good and evil in Babylon, 6th century BC. Their brand of monotheism let them modify much of its ethical idealism. Inspired by Zoroastrianism, the wisdom literature of the Jews consisted of the books of Job. Where were you when I laid the foundations of the earth? Psalms. Yeah. Though I walk through the valley of the shadow of death, I will fear no evil, for you are with me. Your rod, and they comfort me. And the Song of Solomon. Who is she that looks forth as the morning, fair as the moon, clear as the sun, and terrible as an army with banners? Zoroastrian idealism, with its hereditary miscellany of angels and demons, has greatly influenced Judaism, Christianity, and Islam. From the early 5th century BC, with the fall of Babylon, until the time of St. Augustine of Hippo in the late 4th and early 5th centuries, the Mediterranean world was exposed to Zoroastrianism through its derivative religions of Mithraism and Manichaeism, and by its infiltration of Greek philosophy, Jewish prophetic literature, and Gnostic and Neoplatonic theologies. Augustine, who molded Western Catholicism, was at first a Manichaean, and after his conversion he blended Zoroastrian ideals and Greek logic with Judaic scriptural history. In The Eternal City, Augustine compared the heavenly and earthly cities and contrasted otherworldliness and the way of grace and salvation with worldliness, evil, and damnation. Edward Harrison, Masks of the Universe. Human tides have washed across the globe, crushing nations and carving out empires, led by God-inspired men who sought to write their will across the sky and stars. One such leader was Alexander the Great, who crossed the Hellespont in the 4th century BC, subjugated Asia Minor and Egypt, vanquished the armies of the Persian Empire with his cohorts, quelled the turbulent forces of Afghanistan, crossed the Hindu Kush, and invaded and defeated the nations of the Punjab. Eastward flowed Hellenic science and philosophy in the wake of Alexander's conquests. Westward flowed Oriental philosophy and religion. Westward into the Mediterranean world came the Zoroastrian Lord of Light, the glorious Ahura Mazda, embattled with the Lord of Darkness, bringing the belief that the soul is divine and the worship of gods apart from the appointed one a sin. Westward into the Roman legions came the religion of the dying and resurrected martyred god, the triumphant Mithra, bringing the sacramental eating of the flesh of God, and the notion that evil is the privation of good. Westward came the Babylonian story of creation and the flood, the Persian stories of heaven and hell, the last day of judgment, and the resurrection of the dead. All these stories reshaped the theology of the Greco-Roman world, paving the way for the rise of Christianity. Edward Harrison, Masks of the Universe. And we must not forget that westward came ethically inspiring cults, such as the Divine Mother, Isis, holding her child. Tracing the evolution of ideas in the long Middle Ages leads the historian into a labyrinth of confusing ideas. Medical wisdom and learned alchemy made the works of 8th century court physician Jabir ibn Hayyan and Caliph of Baghdad, renowned for the 1001 Nights, especially well known. Jabir was later Latinized into Geber, and because of the rigmarole and obfuscation of the numerous works attributed to him, the word Geberish eventually became gibberish. Edward Harrison, Masks of the Universe. The same principles applied to the macrocosm, the universe, and the microcosm, the individual, in alchemy and astrology. This was the great analogy. The chemical elements and the parts of the human body corresponded with the planets and other heavenly bodies. Silver was associated with the moon, quicksilver with Mercury, copper with Venus, gold with the Sun, iron with Mars, tin with Jupiter, and lead with Saturn. Roger Bacon, 1220–1292, wrote, "Machines for navigation can be made without rowers so that the largest ships on rivers or seas would be moved by a single man in charge with greater velocity than if they were full of men." He foresaw with prophetic vision the development of telescopes, submarines, steamships, automobiles, and flying machines. Furthermore, one can create vehicles that can move with amazing speed. Furthermore, flying machines can be constructed so that a man sits amid the machine, revolving some engine by which artificial wings are made to beat the air like a flying bird. Europe was in the throes of a technology revolution, with the introduction of stirrups, heavy ploughs, water mills, windmills, textile mills, magnetic compasses, gunpowder, pattern-welded steel and paper-making. Bacon's extrapolations were not so fanciful given the contemporary technological developments occurring 5 centuries before the Industrial Revolution. It has not consistently been recognized that the technology revolution occurred not in the 18th, 19th, or 20th centuries, but in the high Middle Ages of the 13th century. Many developments, stirrup, watermill, windmill, gunpowder, paper-making, and magnetic compass, came from outside Europe, but Europeans were the first to apply them widely and make technology a fundamental part of society. See Science in the Middle Ages, David Lindbergh, editor. William of Ockham, about 1280–1349, an Oxford scholar at Merton College, opposed the Platonic philosophy that ideas are the actual reality. He said ideas are often empty names, and the actual realities are the objects. His viewpoint has been summarized in the words, "Entities must not be needlessly multiplied." People often interpret this principle, known as Occam's razor, as the preferred theory with the fewest and simplest assumptions, or ideas. Occam used this argument to criticize Aquinas's theological elaborations of the Aristotelian universe. Occam's razor is helpful in cosmology when comparing rival universes. The preferred universe explains the observed world using the fewest and simplest ideas when all other factors remain equal. Dante Alighieri, in the early 14th century, while a political refugee from Florence wrote the epic poem The Comedy, divine was added later to the title in the 16th century. In this imaginative poem, he placed the angelic spheres of the old Gnostic and Neoplatonic cosmologies in the Empyrean, arranged in such a way that the realm of heavenly spheres and celestial spheres mirrored each other. In his unified model, God became the center of a theocentric realm. The earth remained the center of a geocentric realm. And God and earth were the antipodes of each other. Dante's exceptional amalgamation of the material and spiritual realms arrived later and never found its way into the mainstream of cosmology. Only a few decades previously, in 1277, the notion of God confined to a fixed place in space had been condemned as contrary to orthodox doctrine. In two great systems of the world, Galileo defended the Copernican system's merits in a functional debate with an imaginary Aristotelian named Simplicius Alfred Whitehead. Science and the Modern World writes, Galileo keeps harping on how things happen, whereas his adversaries had a complete theory about why things happen. Unfortunately, the two theories yielded different outcomes. Galileo insists on irreducible and stubborn facts, while Simplicius, his adversary, offers entirely reasonable arguments, at least to himself. To conceive this historical revolution as an appeal to reason is a significant error. It was essentially rather an anti-intellectual movement. Driven by a reaction against the strict logic of medieval thought, it signaled a return to considering brute facts. Making this comment only summarizes what, at the time, the supporters of the previous government claimed. Ideas of space and time were hazy in Aristotle's day and had not yet been sharpened into their contemporary forms. Space came to be connected with the distribution of objects directly seen. On the other hand, things spread in time were not directly observable, and general interval of time were not easily measured. It was unclear how to define motion by combining space and time intervals. Thus, the motion was not very different from other kinds of change. Aristotle's law of motion may be expressed in terms of relation applied force, 1-4 resistance x speed. He had no exact method of measuring force, resistance and speed, and no general formula. He argued qualitatively, drawing on daily experience, that effort is required to sustain a state of motion. The faster the motion, the more effort required to sustain that motion. Inspired by this idea, it seemed natural to conclude that bodies of unequal weight fall through air at different speeds. A body will move through a given medium in a given time, and through the same distance in a thinner medium in a shorter time, said Aristotle, and will move through air faster than through water. Moreover, without all opposition, a body would move from place to place in no time, that is, at inefficial speed. Therefore, maintained the Aristotelians, a vacuum cannot exist in nature, since a body in a vacuum would encounter no resistance, and every force would produce an inefined speed. So space was occupied everywhere by solid, liquid, or gaseous molecules that gave it a significant reality and controlled the motions of moving bodies. Later, the Epicureans, known as the atomists, asserted that atoms travel freely across the void at exact speed. Aristotle responded, "What can be the cause of their motion?" The atomists say there is always movement, but they do not explain why or what it is, or tell us the cause of the motion if we grant atoms exist. Later on, René Descartes expressed similar ideas and said, "A vacuum is repugnant to reason." Aristotle's common-sense law of motion survived, until finally eclipsed by the Newtonian law of applied force 1/4 mass x acceleration, 2,000 years later. Impetus, or momentum. We cannot assume Galileo's brilliance produced the great leap from Aristotle to Newton. Philoponus in the 6th century discussed impetus, now known as momentum. This idea originated with Hipparchus in the 2nd century BC scholars in the High and Late Middle Ages. Including Roger Bacon and Robert Grosseteste, developed the now familiar definitions whereby acceleration is the speed change in an interval, and speed is the distance travelled in an interval. Bodies of different weight, they said, descend with equal acceleration. They illustrated the nature of motion with graphs and diagrams. Scholars of Merton College, Oxford, including William Heytesbury, demonstrated in the 14th century that should v show speed at any moment and represent a constant positive acceleration. Their computations, using graphical techniques, expected Newton and Gottfried Leibniz's discovery of calculus 300 years hence. William Ockham, also of Merton College, maintained that forces might operate remotely without direct body interaction. French philosopher John Buridan, who studied under Occam and then taught Nicolas Oresme, hypothesized that impetus was proportionate to a body's speed and mass of matter. Buridan claimed that driven by their impetus, the planets move independently within their orbits. We now refer to quantity of matter as mass and express impetus or momentum as mv, where m represents mass. A thrown stone's momentum keeps moving. Air resistance gradually slows it down. Without the idea of impetus, Aristotelians reasoned that forces always drove moving bodies. Pushing from behind, they believed the air displaced at the front of a moving body moved to and maintained it in motion. Buridan and his successors maintained that separately dropped bodies falling vertically gain equal amounts of impetus in equal time intervals. Renowned Italian artist, scientist, and engineer Leonardo da Vinci wrote in the 15th century on topics including the Earth's rotation, the history and source of fossils, and the impossibility of perpetual motion. He advanced the theory that bodies descend with an accelerating constant acceleration unrelated to weight. The late 16th century Dutch-Belgian scientist Simon Stevens carried out the experiment. Galileo later credited him. He dropped bodies of different weight from a high building and discovered they landed at about the same moment. French philosopher Pierre Gassendi dropped stones from the top of a ship's mast early in the 17th century to demonstrate that, even when the ship was moving, the stones always landed at the foot of the mast. Ptolemy remarked that a person jumping would not land in the same place if the earth turned. This meant that someone leaping from the deck of a moving ship would not find themselves back on the same deck. Ptolemy was wrong, according to Gassendi's experiments. The 22-year-old clergyman Jeremiah Horrocks demonstrated how the moon travels in a Keplerian elliptical orbit around Earth. He maintained that the movement of the moon was disturbed by the influence of the far-off sun. He proposed that the planets disturb one another's orbits and anticipated the concept of universal gravity. Galileo Galilei compiled, without credit, medieval discoveries about space, time, and motion in his lectures and writings. Balls rolling down inclined planes showed that free-falling bodies in Earth's gravity have constant acceleration. He also showed that impetus is conserved in freely moving bodies. He clarified that the length of a pendulum determines its period rather than its bob weight. He timed intervals using his pulse or the flow of a water jet. Though he ignored Kepler's work and did not theorize about planetary motions, Galileo fervently supported the Copernican heliocentric system. He thought a planet following a heliocentric circular orbit moved naturally in this way without a force dragging it toward the sun. He failed to realize a body following a circular orbit has constant acceleration toward the center of the orbit. Italian modern Giovanni Borelli speculated on the nature of the sun's gravity using Kepler's observations on planetary motions in light of Galileo's advances. The Cartesian world system. Give me matter and motion. I will construct the universe. René Descartes, Discourse on the Method, 1637. First hostile to Copernicus, this fool, said Martin Luther, wishes to reverse the entire history of astronomy. Leaders of the Protestant Reformation later changed their mind, and science found refuge in Reformation nations from the growing hostility of the Counter-Reformation. For a further 200 years, Rome stayed fixated on geocentrism. The northwest nations of Europe rejected geocentrism and quickly turned away even heliocentrism. Then, in the 17th century, two significant world systems arose that mechanically and mathematically reflected the universe. René Descartes, 1596-1650, René Descartes, eminent French mathematician and philosopher, had broad influences on all spheres of knowledge. driven by the Platonic principle, what is reasonable must be true, and the Aristotelian approach, rightly conducting the reason. He produced a grand and all-encompassing system of natural philosophy, more creative than any since antiquity. Its most salient characteristics were the unambiguous dichotomy between body and mind, and the mathematics of the physical sciences. In some respects, his ideas on the nature of space, time, and motion and enunciated laws of motion matched the Newtonian laws of a few decades later. Only God can be infinite, wrote Descartes in his Principles of Philosophy while living in the safety of Protestant Holland. And he would therefore refer to the spatial extent of material things as indefinite, rather than infinite, to reserve to God alone the name of infinite. In the Aristotelian system, space had ended at the sphere of fixed stars. In the Cartesian system developed by Descartes, it extended indefinitely and was strewn throughout with stars and their planets. In the mechanistic Cartesian system, continuous matter of varying density suffused every part of indefinitely expanded space. In the Aristotelian system, matter and ether suffused every part of finite space. Descartes' mechanized universe of matter and motion followed natural laws. We may well believe, without doing outrage to the miracle of creation, that by this means alone, all things that are purely material might in course of time have become such as we observe them to be at present. All forces, he thought, acted by direct contact, that is, between bodies touching one another. Opposite reason, hence impossible and reminiscent of the etheric forces of medieval mysticism, forces operating at a distance without direct material contact were contradictory. Real forces pushing and dragging under pressure and tension controlled all motion. Planetary orbits in the Cartesian world system came from the vortical motions of interplanetary matter. Gravity was the pressure generated by whirling fluids. Reason convinces us. Space itself is nothing. It has no extension. How might space and nothing have height, width, and length? Only matter exhibits extension. Space does not exist where there is nothing. Everywhere exists matter of all kinds at all densities. The vacuum, repugnant to reason, said Descartes, exists nowhere. In Cartesian science, the non-existence of undressed space, the vacuum, was a cardinal idea. From this idea developed Descartes' firm belief on the impossibility of the atomist theory. Direct contact's principle of action demanded voids, continuity of matter, and infinite divisibility absent from other principles. If they exist, atoms by nature would be separated by voids. How else could they be atoms? As voids are repugnant to reason, atoms are physically impossible. Among the first to exhibit the Cartesian duality of body and mind's startling effects, Thomas Hobbes wrote in his book Leviathan in 1651, a year after Descartes passed away. For what is the heart but a spring, and the nerves but so many strings, and the joints but so many giving motion to the whole body? With its physical brain, the human body fit the clockwork universe of matter and motion. The mind was merely a ghost, stalking the machinery of body and brain. How might an immaterial mind affect or control a physical body? Thus started, in unambiguous mechanical terms, the Cartesian duality of body and mind, an unresolved issue still today. Christian Huygens, 1695. Christian Huygens is a pillar of Cartesian science and philosophy, a Dutch physicist and astronomer. He is most known for creating the pendulum clock. He also improved the design of telescopes. He found the rings around Saturn. Mechanical clocks on church towers were until recently as accurate as ancient candle and water clocks. The pendulum-regulated clocks developed by Huygens made marine navigation and scientific investigations far more exact. Descartes grasped the idea of accelerated motion, which Galileo had missed. Motion with non-straight line trajectory. Huygens demonstrated that where v is the speed and r is the circle's radius, there is an acceleration of v2r toward the center in a circular motion. Whirled around, the string dragging on a stone at the end constantly accelerates it toward the hand. Like Descartes, Huygens held that space was a property of matter, and that vortical pressure generated gravity. Opening the age of reason. The Cartesians held that forces interacting in direct contact pushed and pulled everything in an infinite universe. Everything ran based on logic. The liberating and exciting Cartesian philosophy quickly captured the imagination of freethinkers everywhere, despite strong resistance from scholars imprisoned in ancient doctrine and clergy steeped in biblical literature. The Cartesian system cleared the path for the 18th century Age of Reason, sometimes known as the Enlightenment, as the telescope, the microscope, the thermometer, the barometer, and pendulum clocks were developed, and Descartes started to doubt everything except the irreducible. I think, thus I am. It set off the intellectual explosion in England, producing the Newtonian system. The Newtonsian world system. I do not define time, space, place, and motion as well known to all. Principia, Isaac Newton's 1687. At first, English liberal theologians and philosophers viewed Descartes as a savior from medieval mysticism. But soon his philosophy received more criticism than praise. The Cambridge theologian Henry More, initially impressed with the vision of a universe of natural laws, aghast at the implications of Cartesian materialism in later years, returned to the medieval idea that space exists without matter due to the presence of ubiquitous spirit. More favored the idea, shared by many colleagues, of a finite stoic cosmos of stars surrounded by an infinite mysterious void. Isaac Newton also shared this view of the universe. Robert Hooke, 1635–1703. Robert Hooke, Christopher Wren, and Edmund Halley outlined qualitatively what Newton later explained quantitatively. A freely moving body, as explained by Descartes, travels at constant speed in a straight line when nothing forces it from that natural state. Because the planets move not in straight lines but in curved orbits about the Sun, they must be continually pulled by the Sun's gravitational force. Hooke demonstrated the idea with a conical pendulum, figure 3.8, and said mechanical principles can explain planetary motions. At about the time when Newton was silently pondering these matters, Hooke, a scientific genius, perhaps the most inventive man who ever lived, writes Edward Andrade, realized that the force controlling the solar system, which draws the planets to the Sun and the Moon to the Earth, is the same as that which causes apples to fall from trees. I shall explain, wrote Hooke, a system of e-world differing in many particulars from any yet known, answering in all things to the common rules of mechanical motions. The gravity that, in Pythagoras' sphericity of the Earth, was plausible. People on the other side could not fall, had become a universal force in control of the heavens. That all celestial bodies whatsoever have an attraction or gravitating power to their own centers, whereby they attract not only their own parts, and keep them from flying from them, as we may observe the Earth does. Isaac Newton, between 1642 and 1726. The most eminent of all the scientists, Isaac Newton compiled the ideas of many intellectuals since the Middle Ages. He developed the dynamic theories of motion and universal gravity, and built a system that attained the power and elegance to which science had aspired from the beginning. During his early years at Cambridge, in response to Descartes' philosophy, Newton wrote in an unpublished manuscript, referred to by its opening words, de gravitation, that an infinite and eternal divine power occupies all space and extends infinitely in all directions. Descartes claimed that where there is no matter, there is no space. On the contrary, Newton said that where there is no matter, spirit alone endows space with extension. To say that space cannot exist where there is no matter denies the presence of spirit and, hence, the presence of God in the universe. Newton's ideas about the nature of space changed very little in his lifetime. Descartes claimed that matter extends indefinitely. On the contrary, said Newton, in infinite space. God had created a material system of finite extent. Newton's Stoic notion of a finite cosmos of stars changed abruptly 25 years later, in response to questions by the theologian Richard Bentley. Like Descartes, Newton remained single all his life. Most biographers have neglected Newton's scientific subjects and failed to mention that he spent many years absorbed in scriptural studies and engaged in alchemical activities. Newton was appointed Lucasian Professor of Mathematics at Cambridge University at age 27 and resigned 32 years later in 1701. Natural philosophy. Mathematical ideas, Hooke's holistic vision foresaw the rise of the Newtonian mathematical universe. The astounding genius of Newton, meditating for many years on the natural philosophy of space, time, and motion, transformed all previous graphical descriptions into mathematical prescriptions. In his mathematical principles of natural philosophy, known as Principia, Newton said of space, absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Of time, he said, absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. He said, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. We understand. Newton's idea of tonsure space, but not his idea of absolute time. What does the flow of time mean? Chapter 9. The three laws of motion proposed by Newton are, unless driven to change its state by an applied force, a body keeps in a state of rest or constant motion in a straight line. We must note that velocity has magnitude, speed, and direction, and a body's momentum, velocity, is constant without an applied force. If the mass is constant, the rate of change of momentum equals the mass rate of change of velocity, and the law of motion becomes applied force 1/4 mass x acceleration. Else, the rate momentum changes in time equals the applied force, and is in the direction of the force. The third law generates the idea of inertial force. Every force has an equal and opposite force at the same place and time. For example, an equal and opposite force in the ground pushing upward shapes a person's weight. The sum of all forces at any one point is 0. The forces operating on a freely moving body thus equal 0. The inertial force is the force experienced during acceleration, and is opposite, in direction to the acceleration. In circular motion, a body's acceleration is toward the center, whereas the inertial force, in this case the centrifugal force, is directed away from it. A stone whirled around at the end of a string length has a centrifugal force that pulls outward, and is equal and opposite to the tension in the string that pulls inward. The third law explains why, in a spaceship orbiting the Earth, an astronaut is weightless and does not feel the pull of the Earth's applied force of gravity, and the inertial force caused by the spaceship cancels gravity. The remarkable thing about the Newtonian laws is that a freely moving body follows a trajectory on which the inertial force cancels gravity, and the body experiences no force. The sun's pull is imperceptible to us on Earth due to the Earth's orbit. Einstein stated that the principle of equivalence is vital in developing the theory of general relativity, according to which freely moving bodies follow trajectories as if gravity does not exist. Thus, a person in free fall, such as an astronaut in a spaceship, experiences no gravitational force. But beware of tidal forces. Absolute and relative motion in the Newtonian world Motion is both relative and absolute. When the velocity of an automobile is constant, we feel no inertial force. We measure its constant velocity relative to other vehicles or stationary objects at the side of the road. No matter the relative velocity, no inertial force exists as long as it stays constant. A passenger with closed eyes and unable to hear cannot determine the automobile's use. The velocity is purely relative and has no absolute value. When the velocity changes, however, a force exists, the inertial force, that we feel during acceleration. And this force is not produced by motion relative to anything. Notice, in the Newtonian system, acceleration means a change in velocity, speed, direction, or both. The passenger with closed eyes estimates the acceleration based on the magnitude and direction of the experienced inertial force. When speed only changes, the inertial force is directed forward, if speed decreases, or backward, if speed increases. When only the direction changes, the inertial force is directed toward the left, when turning to the right, or toward the right, when turning to the left. The physical properties of Newtonian space are such that uniform velocities are relative, measured relative to, and changes in velocity, accelerations, are absolute, measured relative to nothing. The situation remains the same in modern relativity physics. Uniform velocity is relative, and acceleration is absolute. Universal gravity. The gravitational attraction between any two bodies varies as the inverse square of their separating distance, figure 310. The force pulling a planet to the Sun varies as the inverse square of the planet's distance from the Sun. How did Kepler discover this? Kepler's third law is the clue, CP 107 for Kepler's laws. Kepler's planet moves about the Sun in a circular orbit of radius r at speed v. The acceleration toward the center of the orbit is v2rr, as Huygens shows. Hence, the inertial force directed away from the center is mass acceleration, or mv2r, where m is the planet's mass. The planet's gravitational pull of the Sun must be equal and opposite to the centrifugal force experienced by the planet. In Newton's world, all bodies attract one another with gravitational forces proportional to their masses and the inverse square of their separating distances. Newton demonstrated that a spherical body exerts a gravitational attraction, as if all its mass were concentrated at the body's center, and that the natural orbits of planets are ellipses, parabolas, or hyperbolas. As a professor of mathematics at Cambridge University, Isaac Newton gave 8 lectures a year, which few students attended. His monumental work, The Mathematical Principles of Natural Philosophy, was written in less than 2 years, published in 1687 at Halley's encouragement, and sold for 7 shillings a set. With a few definitions and axioms and an array of propositions, Newton proceeded to explain mathematically the twice-daily tides on Earth caused by the Sun and Moon, the flattening of the Earth at the poles owing to its daily rotation, the precession of the axis of the Earth's rotation every 26,000 years, due to the equatorial bulge of the Earth, the perturbations of the Moon's orbit, and the paths of the planets and comets. He and Gottfried Leibniz, a German mathematician and philosopher, independently developed the mathematical principles of calculus. Newton and the infinite universe Bentley letters. In his will, Robert Boyle left an endowment to support an annual lectureship to combat the atheism widely professed by wits in coffeehouses and taverns. In 1692, Robert Boyle selected young Richard Bentley, an erudite clergyman, to deliver the first series of lectures. In his last 2 lectures, entitled A Confutation of Atheism from the Origin and Frame of the World, he showed how the marvels of the Newtonian system gave indisputable proof of the existence of a divine power. He argued that the laws of nature alone were insufficient to explain the wonders of the natural world, and must be supplemented by acts of divine power. Before publishing his lectures, Bentley took the precaution of consulting Newton on several technical points. His deep and disturbing questions jolted Newton into rethinking his cosmological ideas, and Newton's 4 letters to Bentley rank among the most critical documents in the history of cosmology. First letter, December 10th, 1692. In the first letter, Newton answered Bentley's question on the effect of gravity in a finite system of stars and stated that a universe built of self-gravitating matter is inevitably unbounded. Otherwise, all matter would fall down to the middle of the whole space, and there compose one great spherical mass. But if the matter were equally distributed over infinite space, it would never form one mass, but rather an infinite number of great masses scattered over infinite space. The sun and fixed stars could perhaps arise from this configuration. Newton so turned from the Stoic universe to an Epicurean-like one. Second letter, dated 17th of January 1693. Newton had entirely agreed with Bentley that gravity meant Providence had created a universe of great accuracy. "You argue," said Newton in his second letter, "that every particle of matter in an infinite space has an infinite quantity of matter on all sides, and by consequence, an innate attraction every way, and so must rest in equilibrium. It's hard to believe that all the particles in infinite space are perfectly aligned. The task is as hard as making only one needle, but an infinite number of them, as many as particles in an infinite space, stand precisely poised upon their points. Yet I grant it possible, at least by divine power, and if they were once so placed, I agree with you that they would continue in that position without motion forever unless put into motion by the same power. When, therefore, I said that matter evenly spread through all spaces would convene by its gravity into one or more great masses, I meant matter that is not perfectly balanced or at rest. So then gravity may put the planets into motion, but without the divine power, it could never put them into such a circulating motion as they have about the sun. And therefore, for this as well as other reasons, I am compelled to ascribe the frame of the system to an intelligent agent." The third letter, dated February 11th, 1693, Newton developed earlier arguments that a divine power was necessary to design the initial conditions. The hypothesis of deriving the frame of the world by mechanical principles from matter evenly spread through the heavens being inconsistent with my system. I had considered it very little before your letters put me upon it, and so trouble you with a line or two more about it. Fourth letter, dated 25th of February 1693. Newton once more reassured Bentley that his mechanical view of the world did not exclude of a divine power to preserve it. This frame of things could not always subsist without a divine power to conserve it, global gravitation. The Newtonian theory of universal gravity, in which all bodies attract one another, strengthened the growing belief that the universe must be edgeless and hence, according to Euclidean geometry, inaffine. Said Newton, a finite universe limited by a cosmic edge would have a center of gravity. The attraction between its parts would cause them to fall down into the middle of the whole space, and there would be one great spherical mass. This argument caused him to abandon a finite Stoic universe in favor of an infinite Epicurean universe. Newton wrote, "The fixed stars, being equally spread out in all points of the heavens, cancel their mutual pulls by opposite attractions. Each particle of matter, pulled equally in all directions, remains in equilibrium in an inine uniform universe." Published after the Bentley letters, Newton's second edition of the Principia, but an unstable equilibrium, as Bentley noted. The theory of universal gravity supported the belief that the universe is stationary on the cosmic scale, and started the idea that on smaller scales, gravity caused matter to condense and form astronomical bodies such as stars and planets. Atomic theory, inspired theory, atomism, did not become popular in science until the 17th century. Pierre Gassendi, a French natural philosopher of that century, revived atomist theory, despite residual Aristotelian objections, and its connection with Epicurean atheism. The theory was rather important in the mind of men like Robert Boyle, Otto von Guericke, mayor of Magdeburg, and Newton. Newton interweaved the old atheistic atomic philosophy into the modern religious doctrine and triumphed by compromise in his book Optics. It seems probable to me that God in the beginning formed matter in solid, massy, hard, impenetrable particles of such size and figs, and with such other properties, in such proportions to space, as most conduced to the end for which he formed them, even so very hard as never to wear or break in pieces. There are 4 agents in nature able to make the particles of bodies stick together with extreme attractions. And it is the business of experimental philosophy to find them out, he said in prophetic words. Today, we have high-energy particle accelerators for this use. Reviews from Classical Antiquity. 3 world systems survived and laid the foundation of European natural philosophy in the 16th and 17th centuries. The Aristotelian system of geocentric celestial spheres consisted of planetary orbits inside a sphere of XZ stars. Medieval editions surrounded the sphere of XZ stars, where God dwelt and populated the celestial spheres with angelic beings. This was the conventional Judaic-Christian-Islamic cosmology. The Epicurean system comprised a finite void filled with uniformly spaced worlds made of atoms under control by natural laws. Descartes changed this system by denying atom existence and applying it with matter. Following his correspondence with Bentley, Newton adopted this method with spirit and maintained its atomicity. Declared the Athenian playwright Aristophanes in the 4th century BC, "Whirl is king." Early science was dominated by vortex scenarios. Whirlwinds and whirlpools had great roles in mythology. Many philosopher-scientists thought the stars and planets developed from a primordial vortex. The idea of whirling fluids in big and tiny vortices was core to the Cartesian system. Newton's proving that planetary orbits could be explained by gravity and the laws of motion finally caused the Cartesian vortex theory to be abandoned. Chapter 4's developing theory of swirling matter into the solar nebula was developed by Immanuel Kant and Pierre-Simon de Laplace. Whirl is king of our cosmogonic star and galaxy creation models even now. I do not suggest that matter and space are the Gottfried Leibniz, 1646-1716, wrote in a letter to Samuel Clarke, who argued in favor of Newton's ideas and the reality of an absolute space independent of matter. Leibniz shared the Cartesian belief of many continental philosophers that space is meaningless. He also shared the Cartesian belief that forces could not act at a distance unless conveyed by a material media. Kepler's third law, for example, in these units reads P2 R1, where P is the period and R is the radius of an orbit. The universal gravitational constant, nowadays denoted by G, does not appear in units that measure masses in solar masses, m8. Distances are measured in astronomical units. An astronomical unit is the distance from the Sun to the Earth. And time intervals are measured in years. Lucretius contended in Book 1 of De Rerum Natura that space is in flux and unbounded. If all the space in the whole universe were closed in on all sides, with fixed boundaries, then all matter, because of its weight, would have flowed together from all sides and sunk to the bottom. Nothing could be carried on beneath the canopy of the sky. Indeed, there could be no sky nor sun, since all matter would be idle, piled together over unbounded time. But since everything moves ceaselessly, the universe has not been granted such rest. No bottom exists where matter can flow from all sides and settle. Translated from T. Lucreti, Cari, De Rerum Natura. Lucretius's argument anticipated Newton's reasons for believing in infinite space. By drawing on the idea of ceaseless movement, the Epicurean poet vaguely realized what Newton and Bentley omitted to discuss: the possibility of a finite system of moving stars in stable equilibrium, as in a galaxy. They agreed that stars stretch away endlessly, as in the Epicurean universe, and believed, on the other hand, that if the material system were finite, as in the Stoic universe, the stars would fall into the middle of the system. However, a static Stoic cosmos can exist in a state of equilibrium. Stars in a galaxy do not fall into the middle, but move freely around the center in various orbits. A cluster of stars in equilibrium obeys what is known as the virial theorem. Depends on the way mass is distributed in the cluster. For a cluster of uniform density, a 3-to-5. Stars move in various orbits about the cluster's center of mass, and need not fall into the middle, as Newton advised. The Victorian one-island universe, Chapter 4, a single giant galaxy in an infing vacuum, obeyed the virial theorem. Published Letters from London on the English. Voltaire fled from France to England for 3 years to escape his enemies, the victims of his uncompromising wit. A Frenchman coming to London, wrote Voltaire, finds matters greatly changed in philosophy and everything else. Cartesian and Newtonian systems, said Voltaire. He leaves the planet filled. He finds it empty here. Whereas in London, nothing is seen of the universe made of vortices of a subtle matter found in Paris. With us, the pressure of the moon causes the sea's tides. With the English, the sea gravitates toward the moon. Furthermore, you could find that the sun, which in France is not involved in the air, has to help by almost 1/4. With your Cartesians, everything takes place through pressure, which is not easily understandable. With Monsieur Newton, it takes place through attraction, the cause of which is not better known either. Determining the distances to stars is not easy. A Dutch astronomer, Christiaan Huygens, used a crude photometric method in the late 17th century. He assumed that all stars are similar to the sun. He observed the sun in a dark room through a small hole in a screen covering the window. By adjusting the size of this hole until its brightness matched that of Sirius at night, he estimated Sirius to be 30,000 astronomical units away, or roughly 0.5 light-years. This method depends on judging in the daytime how bright Sirius is at night. The young Scottish astronomer James Gregory, unknown to Huygens, had some years previously proposed a photometric method that did not depend on memory. Gregory assumed that the nearby bright stars were sun-like, and compared their brilliance with that of the outer planets Mars, Jupiter, and Saturn. Knowing the sizes of the planets and their distances from the Sun and Earth, and making allowance for the imperfect reflection of sunlight from their surfaces, he estimated the distance of the nearest stars as several hundred astronomical units. Isaac Newton referred to Gregory's method in his System of the World, and in unpublished work, placed the brightest stars at 500,000 astronomical units, or roughly 8 light-years. This estimate was a remarkable anticipation of more recent measurements. 8. This most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being. And if the FXZ stars are the centers of other like systems, these being formed by informed wise counsel, they must all be subject to the dominion of one. O. H. Newton, Principia, 2nd edition, translated by Andrew Mott, pages 389, 390. Whence is it that nature performs nothing in vain, and whence arises all the order and beauty in the world? Isaac Newton's Optics. Mortales. Revoice is quite wonderful for the human race. The words show on Newton's tomb in Westminster Abbey. Astronomical developments in observation and theory were initially slow following Newton. Better telescopes were still to be created. Spectroscopy and photography were adopted into astronomy. Star and nebulae chemical compositions and radial velocities were established. Distance indicators to be found and calibrated. Globular clusters to be identified as systems of stars laying in and on the outskirts of the galaxy. Nebulae in the galaxy to be distinguished from extragalactic nebulae. And the perplexing obscuration of starlight caused by interstellar absorption still unresolved. All of this would be achieved along with the ongoing discussion over divisive problems from Newton to the time of Einstein, during the 18th, 19th, and early 20th centuries. Hierarchical universes. Those who live in deserts, sail the oceans, or live in out-of-the-way locations far from city lights know why the night sky was so significant to people of past times. On clear, moonless nights, the Milky Way, the Via Lactea, arches wraith-like across the sky, and the vault of heaven swarms with brilliant stars and nebulous lights. At the beginning of the 18th century, stars uniformly permeated the centerless, edgy Cartesian and Newtonian systems. However, as astronomers extended their horizons and built better telescopes, it became more difficult to overlook the apparent fact that stars were not evenly distributed over the sky. Thomas Wright of Durham had fresh ideas about the Milky Way that he offered in his book, An Original Theory of the Universe, printed in 1750 in northern England. Wright's universe included a supernatural galactic center. First, he said, he had expected the stars to be promiscuously distributed through the mundane space. But later, because of the Milky Way, he realized that the stars were scattered in some regular order. At this center of creation, he would willingly introduce a primitive fountain, perpetually overflowing with divine grace, from whence all the laws of nature have their origin. He suggested two possible constructions of the Milky Way system: either a ring-shaped distribution of stars encircling the center, similar to the rings encircling Saturn, or a spherical shell of stars, concentric with the center, in which the Milky Way consists of the stars seen in a plane tangential to the shell. Wright ventured farther and speculated on the several possible centers of creation. Like our Milky Way, the far-off nebulae seen as faint and fuzzy skylights may be other creations, or abodes of the blessed. The unceasing immensity is a plenum of creations not unlike the known universe. Reviewing Wright's work, German philosopher and scientist Kant concluded that the Milky Way is surrounded by far-off similar Milky Way systems, and that the Milky Way is a disc-shaped or lens-shaped distribution of stars. In his Theory of the Heavens, Kant offered 1755 a scholarly interpretation of Wright's ideas. According to Kant, the Milky Way's stars create a rotating disk together by gravity. The fuzzy nebulae are like rotating Milky Way systems. It is natural to assume that these nebulae are systems of numerous suns, which appear, because of their stance, crowded into a space so limited as to give a pale and uniform light. Their analogy with our own system of stars, their shape, which is just what it should be according to our theory, and the faintness of their light, which denotes great distances, are in admirable agreement, and lead us to consider this elliptical spot as systems of the same order as our own. Kant said these Milky Way, now called galaxies, are perhaps clustered, forming vast systems of many galaxies. These great systems, he hypothesizes, are grouped together to create even vaster systems, which are clustered together to create yet more extensive systems, and so on, throughout infinite space. Figure 4.5. Each level of such a cosmic hierarchy consists of an inline array of centers, and the centers at each level form clusters about the centers of the next higher level. We see the first members of a progressive relationship of worlds and systems, and the first part of this infinite progression enables us to recognize what must be conjectured of the whole. There is no end here, but an abyss of absolute immensity. in which all the capability of human conception sinks exhausted. The ultimate center dominated the structure at the highest level of infinite order. Swiss-German mathematician Johann Lambert entertained like ideas. In Cosmological Letters, Lambert wrote in 1761, "The eye, assisted by the telescope, may penetrate all the way to the centers of the Milky Ways, and why not even to the center of the universe?" His assumption that each center was occupied by a body he referred to as dark regent set the primary difference. The term cosmical island was used in 1855 in the book Cosmos by a restless man with broad scientific interests, von Humboldt, who wrote, "Our cosmical island forms a lens-shaped system of stars." Authors soon popularized cosmical islands as island universes and island universes. Sadly, uncertainty results when galaxies are referred to as worlds. We shall thus refer to galaxies as islands. Hence, a Stoic-like system is a one-island universe and an Epicurean-like system is a many-island universe. The hierarchy is said to be fractal, a term first used by the French scientist Benoit Mandelbrot, when the arrangement on several levels repeats itself. For instance, the irregularities of a coastline, measured on tens of meters, then kilometers, and then hundreds of kilometers, are similar. Stars form clusters, each of n1 stars at the first level. Star clusters form galaxies, each of n2 star clusters at the second level. Galaxies form galaxy clusters, each of n3 galaxy clusters at the third level. Galaxy clusters form superclusters, each of n4 galaxy cluster at the fourth level. And so on. The nebula hypothesis. French mathematician and astronomer Pierre-Simon de Laplace, 1749–1827, showed in his Celestial Mechanics the stability of the planetary system, and so eliminated periodic corrections by a divine power Newton had suggested. Laplace explored the theory that the solar system had developed from a revolving and contracting gas cloud in his non-mathematical and popular system of the world, first printed in 1796. This theory holds that the Sun and planets first condensed from a big whirlpool of interstellar gas, now accepted in modernized form. Maybe other solar systems had developed similarly. Though less focused on the significance of rotation, Kant advanced the same idea earlier in his book, The Theory of the Heavens. The hypothesis concerning the Kant-Laplacian nebula. For astronomers and natural thinkers, nebula, which means cloud, captivated their imagination. Every hazy bit of light in the night sky in the 19th century became a potential interstellar cloud of condensing gas. Even the massive neighboring galaxy, Andromeda Nebula, like nebulae, evolved conjectural solar systems during formation. Cosmonical islands, the far-off nebulas. As L111 approaches, small, faint, fuzzy patches of light and density decrease with size. Chapter 24 covers fractals more thoroughly. Under the right Kantian interpretation, suppose that 1,000 galaxies, each of size 1, in the night sky, figure 4.8, were distant Milky Way systems of stars, and, under the Kant-Laplacian interpretation, were clouds of gas condensing into solar systems. Whereas the solar system interpretation favored a single island universe, the Milky Way interpretation favored a many-island universe. In a melodrama spanning until the early 20th century, in which astronomers seesawed from one interpretation to the other, these conflicting viewpoints took the front stage. William Herschel, 1738–1822, German-born professional musician, Herschel moved to England at the age of 19. Later, his sister Caroline joined him, and they developed strong astronomical enthusiasm. They resolved many nebulae into star clusters using modern telescopes. William gained recognition as the leading astronomer of the 18th century after his incredible discovery of a seventh planet beyond Saturn, subsequently known as Uranus. Using telescopes of unmatched accuracy and light-gathering capability, The Herschels peered skyward. William presented their findings in books under 3 presumptions. Interstellar space lets starlight through it transparently. Every star resembles the sun rather closely. Stars are scattered evenly over space. All 3 were later found to be in error. The first and second assumptions meant the farthest, faintest stars were the distances. Apparent brightness could be used as a distance measure. The first and third presumptions meant the Milky Way stretched the farthest, where the sky appeared most crowded with stars. These presumptions led the Herschels to map the heavens and discover, from figure 4.9, the Milky Way as a flattened system with the sun close to the central axis. Mostly the result of assumption I, the galactocentric theory, that the sun is at the center of the galaxy, was, at the time, no astronomer was aware of the strong absorption of starlight brought about by dusty gas clouds separating between the stars. William thought that the starless areas of the sky, now known to be caused by obscuring clouds of gas and dust, were holes in the sky through which we view the darkness beyond the Milky Way. The constellation of Sagittarius hides the galaxy from view. The Herschels demonstrated that Kepler's laws match the motions of double stars, 2 stars in orbit about one another. Inspired by the Wright-Kantian hypothesis, William noted in a paper titled On the Construction of the Heavens in 1785 that many nebulae might be exceptionally far-off systems akin to our Milky Way, for which reason they may also be called Milky Ways by way of distinction. In a letter he said he had discovered 1,500 worlds, whole sidereal systems, some of which could well outvie our Milky Way in grandeur. For most of his life, he supported the view that the universe is endlessly populated with galaxies, much like the Milky Way. But the mystery of the nebulae grew more complex, and William became less confident as the Kant-Laplacian nebula hypothesis gained popularity, until he finally voiced the belief that most nebulae might have originated within the Milky Way. His observations of double stars let him realize that stars in general can be pretty different in brightness. The second assumption, that all stars are alike, was untenable. Was the third assumption, that stars are evenly spaced in space, then realized to be somewhat inconsistent? Some nebulous areas, such as Orion, appeared to be a shining fluid rather than a collection of stars, casting questions on the first assumption. William Herschel held that living entities inhabited the moon and planets. It is startling, though, that the most eminent astronomer of the Age of Reason could have thought that a cool surface also inhabited by living entities existed under the sun's brilliant atmosphere. Still, this was before the birth of the new astronomy and the union of physics and astronomy. The new astronomy. Light speed. Descartes was reassured by reason that light moves at a finite speed, and that the world as we know it exists. If the light rays building an image from various distances started at different times, how confused would our reconstruction of the external world be? A finite speed meant that an object seen at the moment of observation had moved elsewhere and changed its appearance. It was not what it seemed. Objects at closer or farther distances would have moved and changed in different degrees. Descartes and many Cartesians, too amazing to be taken seriously, thought that we look back in time when we gaze out into space. However, the Danish astronomer Ole Romer declared at the Paris Academy of Sciences gathering in 1676 that the eclipse of Io, a moon of Jupiter, on November 9th would happen 10 minutes late. His projection drew on past performance. The delay would be caused by the extra distance light traveled to catch up with the Earth, Romer said, as the planet moved away from Jupiter. This accurate prediction helped him to discover the finite speed of light. Updated by Edmund Halley, the findings revealed that light travels a sun-Earth distance, known as an astronomical unit, in just 500 seconds at the incredible speed of 300,000 kilometers a second. Light takes up more time traveling from the stars to us, Francis Roberts, in 1694, in a paper concerning the distance of the fixed stars, said, noting that parallax of the stars caused by the Earth's orbit about the Sun had not been detected, and that stars were, thus, further away than a certain minimum distance. Light travel time is essential in cosmology, and this was its first use as a distance measure. But even the closest stars have far less parallax than Roberts projected, and their light travels years rather than weeks to reach us. James Bradley's discovery of light's aberration in 1729 brought about opposition to the finite speed of light to a stop. Because of the Earth's motion around the Sun, he noted that stars move backward and forward by a slight angle during the year. The angular displacement, independent of star distance, matched Romer's finite speed of light. The umbrella is tipped forward when someone walks in vertically falling rain. The rain slants toward the person's face. The rain's slant is like the slant of light's aberration. In her System of the Stars, 1890, Agnes Clerk, a leading 19th century historian of astronomy, wrote, "For our view of sidereal objects is not simultaneous. Communication with them using light takes time and post-dates the sensible impressions of their whereabouts in direct proportion to their distances. We see the stars not where they are, not even where they were at any instant, but on a sliding scale of instants." A fact of paramount importance in cosmology is that when we look out in space, we also look back in time. And the farther we look out in space, the farther we look back in time. Light rays' directions. Newton asked, "Are not the rays of light tiny bodies emitted from shining bodies?" Robert Hooke and Christian Huygens proposed wave theories of light that explained reflection and refraction, bending of light as in a prism. Even though Newton spoke of ether waves that vibrate like sound waves, or are like the waves on the surface of water. In the early years of the 19th century, physician, scientist, and authority on Egyptian hieroglyphics, Thomas Young demonstrated how the wave theory explained interference, superposed waves of the same wavelength add and subtract, and diffraction, deflection, according to the wavelength of waves passing through an aperture. Outstanding experimental physicist Michael Faraday and brilliant theoretical physicist James Clerk Maxwell investigated and unified electricity, magnetism, and the properties of light, and developed the contemporary theory of electromagnetism in the middle decades of the century. Max Planck and Albert Einstein demonstrated early in the 20th century that light has wave-like and corpuscular characteristics. Radiation particles are now known as photons. William Huggins, 1824-1910. Later known as astrophysics, the new astronomy of the 19th century started when astronomers turned to physics to help in star and nebulae research. The laboratory literally migrated into the observatory, figure 410. William Huggins, who first developed the use of the new technologies of spectroscopy and photography in astronomy and was subsequently much helped by his wife Margaret, was a primary contributor to the latest science. Huggins resolved to treat the stars the same way spectroscopic studies of sunlight had already shown that the sun consisted of the same elements as the Earth. For most of the 19th century, a primary concern in astronomy was the nature of the nebulae, the fuzzy light patches in the night sky. Three choices were presented to astronomers. The nebulae were: A. Far-off galaxies, including our galaxy. B. Gas clouds whirling into stars and planets. C. Groups of unresolved stars inside and outside the galaxy. After William Herschel lost his support, the first possibility, A, was the right Kantian many-island universe. The second possibility, B, was the Kant-Laplacian nebula hypothesis, now rather popular. The third was that many nebulae were clusters of hitherto unresolved stars, a prospect of increasing popularity brought about by the discoveries made with much upgraded telescopes. The possibilities, B and C, matched a one-island universe. A light spectrum from a luminous source illustrates how intensity changes with wavelength. Spectral lines are often bright and dark, narrow areas seen on a spectrum. At different wavelengths, the emission, glowing, and absorption, dark, lines mark the producing and absorbing atomic elements. Working in his home observatory, Huggins matched the spectra of elements excited in spark gap discharges with those of stars, nebulae, and comets. Notice the battery wires and induction coil in Figure 4.10. Huggins finally succeeded and declared the news to the scientific world in 1863. The heavens are made of the same elements as the sun and earth. For many old ideas, this was the death blow. Familiar people started to migrate from the churches to the observatories to understand the starry heavens' character. William Huggins wrote, "I directed the telescope for the first time to a planetary nebula in Draco, and hesitated, put my eye to the spectroscope. Was I not about to look into a secret place of creation? What he saw was not what he expected. 1 year later, in 1864, the riddle of the nebulae was solved. The answer, which came to us in the light itself, read, 'Not an aggregation of stars, but a luminous gas.' The spectroscope displayed not the continuous spectrum characteristic of a hot star, but a spectrum of lines characteristic of an excited. Many had earlier assumed that the enigmatic elliptical and spiral nebulae were not clusters of suns, but rather gaseous nebulae that were contracting to create solar systems by their slow heat loss. Assumption A, the Wright-Kant hypothesis, was dead. Doppler effects. By tracking the change in their spectral lines, Huggins was also the first to determine the radial velocity, the speed away from and toward us. The French scientist Armand Fizeau anticipated and computed this change, now known as the Doppler E effect, in 1848. Fizeau in 1849 also pioneered terrestrial methods of measuring the speed of light. When a luminous source, such as a star or a candle, moves away from an observer, all wavelengths of its radiation are raised, and all frequencies are lowered. Conversely, when the source moves toward the observer, all wavelengths are reduced, and all frequencies are raised as observed by the observer. Huggins, in The New Astronomy, A Personal Retrospect, wrote, "To a swimmer striking out from the shore, each wave is shorter, and the number of waves he goes through in a given time is greater than would be the case if he stood still in the water." Austrian physicist Christian Doppler demonstrated in 1842 that a receding or approaching sound source is heard with a lower or higher pitch than when motionless. He proposed in 1848 that stars in binary systems periodically change their color, becoming blue when approaching and red when receding, and that their motions determine their colors. Fizeau showed this was not the case by making the proper computation. Known in the 19th century as the Fizeau-Doppler effect, the displacement of spectral lines generated by relative motion today, presumably less fairly, as the Doppler effaction. The effaction was difficult until photography developed to the point where dry and sensitive plates could be exposed for hours in clock-driven telescopes. In 1868, William Huggins prophetically wrote of the Fizeau-Doppler effect, to sketch, even in broad outline, the many glorious achievements that surely lie before this method of research in the immediate future. An atomic theory in use today. Beginning in 1803 with John Dalton's book, New System of Chemical Philosophy, which became popular, the modern atomic theory of matter evolved. Dalton was the first person to develop the atomic theory quantitatively and brought the Greek word atom into use in chemistry. He demonstrated that matter consists of atoms of different weights, since elements mix in definite ratios by weight to create chemical compounds. Hydrogen had an atomic weight of 1. On this scale, carbon had an atomic weight of 12, oxygen 16, and so forth. Joseph Thomson found the negatively charged electron in 1897. Ernest Rutherford found the positively charged atomic nucleus in 1911. Niels Bohr built a mechanical model of the atom with electrons in orbits about the nucleus in 1913. And a few years later, Erwin Schrödinger, Heisenberg, and other physicists developed the modern wave mechanical model of the atom using quantum mathematics. Regarding atoms, Bohr observed, language can be used only as in poetry. The Victorian University. The typical cosmological model of the 19th century. The Victorian universe was the standard model of the 19th century during Queen Victoria of Great Britain's reign, 1837 to 1901. Driven by the emergence of modern astronomy, it arrived at its last form near the end of the century. It resembled a one-island universe. By chance, the Sun and Earth were situated in the middle of the galaxy, the continent of the universe, encircled by little islands. Beyond the galaxy stretched an endless mysterious void, more fit for contemplation by theology gains than astronomers. The galaxy, Figure 412, comprised approximately 1 billion stars. Numerous clusters of stars, often unresolved and on the outskirts. And gaseous nebulae, mostly condensing solar systems and planetary nebulae, thrilled a sizable audience in Europe and North America. The many wonders of the Victorian universe, glorified in hundreds of popular astronomy books, were announced from every pulpit. Leading late 19th century astronomer Agnes Clerk captured the consensus view in 1890 in her book, The System of the Stars. She said some nebulae were clouds of spinning gas, some were clusters of unresolved stars, but none were galaxies like our Milky Way. It is safe to say that no competent thinker, with all the data before him, can now maintain any one nebula as a star system of coordinate rank with the Milky Way. All-embracing, that is to say, so far as our capacities of knowledge reach, a practical certainty has been attained that the whole contents, stellar and nebular of the sphere, belong to one mighty aggregation, and stand in ordered mutual relations within the boundaries of one all-embracing scheme. Science has no concern with the infinite opportunities beyond. Inherited by the 20th century, this was essentially the conventional model of the Victorian universe. In some respects, the Victorian universe was the old Stoic one-island universe, updated and rebuilt with stars, planets and gaseous nebulae created of atoms like the solar system. A one-island universe was supported even more by the Stoic solution of the dark night sky riddle. Clarke wrote, "The likelihood is relatively straightforward that the stellar system has quantifiable dimensions. Otherwise, darkness would be banished from our sky, and the intense, inane, glowing with the mixed beams of suns that are individually indistinguishable would bewilder our feeble senses with its monotonous splendor. Every line of sight from the eyes stretched out in space must finally cross the surface of a star in an infinite universe endlessly inhabited by stars. Stars have to cover the whole heavens. Olber's paradox is, why is the sky dark at night? How a limited universe of stars, Clarke discusses, is only one of several possible solutions, which were not accepted 100 years later. The age puzzle. Jews, Christians, and Muslims felt the universe was only thousands of years old until the 18th century. In geology and paleontology, the study of fossils, mounting evidence, revealed a far higher age, and conflicted scriptural records with scientific knowledge. Developed doctrines of compromise whereby the Earth had been periodically visited by disasters, including life-destroying deluges, and supernatural and natural laws had alternated in their management of the planet. Far away and long past. For more than 200 years following Romer's discovery, astronomers tended to overlook the significance of the limited speed of light concerning the universe's age. A small number of exceptions existed. Bolder than most, William Herschel said sometimes that we see the heavens as they were long ago. In 1802, he wrote, "A telescope with a power of penetrating into space like my 40-foot one, see figure 4.7, has also, as it may be called, a power of penetrating into time past. Thus, so many years ago, this object must already have had an existence in the sidereal heavens to send out those rays by which we now perceive it. John Herschel, a pillar of Victorian society, was not a Don Quixote to sally forth and tilt at solidly held religious beliefs concerning the age of the universe. He wrote in 1830 in a treatise of astronomy, "Among the countless multitude of such stars visible in telescopes, there must be many whose light has taken at least 1,000 years to reach us, and that when we observe their places and note their changes, we are, in fact, reading only their history of 1,000 years anterior date, wonderfully recorded." John Herschel was a more cautious man. Not von Humboldt, who wrote in his book Cosmos, "It still remains more than probable from the knowledge that we possess of the velocity of transmission of luminous ray, that the light of remote heavenly bodies presents us with the most ancient, perceptible evidence of the existence of matter. The fundamental fact that we also look back to the beginning was not openly explored in the Victorian universe." In 1901, coincidentally the year Queen Victoria passed, Lord Kelvin did what no astronomer had dared. In On Ether and Gravitational Matter Through Infinite Space, he computed the pertinent relations between the age of the oldest luminous stars and the age and extent of the visible universe. However, evidence from the heavens of the cosmic age came too late. Geologists who demonstrated that the universe's age must be measured not in thousands, but in millions, and maybe even billions of years, had already undermined the cosmochronology of Genesis. Geological Sciences. Scottish farmer and Dr. James Hutton put out in 1785 that mountain formation and erosion are ongoing events spanning an indefinitous period. He concluded from the evidence that no vestige of a beginning, no prospect of an end. This was the beginning of the steady-state uniformitarian principle, powerfully argued by Charles Lyell. The surface remains unchanged, while mountain uplift, erosion, and sedimentation continuously modified the landscape. Presented in 1859 in his book On the Origin of Species by Natural Selection, Charles Darwin's theory of evolution fit into this picture of an Earth of great, if not infinite, age. The uniformitarians hold in a steady-state world, governed by natural laws. The catastrophists, on the other hand, believe in a world routinely visited by disasters. Until the end of the 19th century, the debate between the two schools was far more intense than between the Big Bang and steady-state schools of the 20th century. Under the direction of Lord Kelvin, physicists attacked homogeneity in the second half of the 19th century. Calculations on tidal effects and terrestrial heat losses revealed the Earth could not be as old as the geologists claimed, now known to be inapplicable. The Sun's computed age proved to be the most decisive. Based on Hermann von Helmholtz's theory, Kelvin saw that the Sun's luminosity was driven by gravitational energy liberated during slow contraction. The Sun's age, he calculated, is 20 million years. See Chapter 5. This implied that fossils could not be older than 20 million years, since life on Earth depends on a luminous sun. The physicists' insistence on this brief period caused horror in the Earth and life sciences. Attempts were made to fit geological history and the evolution of life into Kelvin's short chronology. Early in the 20th century, physicists redeemed themselves with radioactive dating techniques and demonstrated that the age of the Earth is billions, not millions of years. The discovery of the radioactive elements, which in their disintegration liberate enormous amounts of energy, thus increases the possible limit of the duration of life on this planet, and allows the time claimed by the geologist and biologist for the purpose of evolution. Ernest Rutherford wrote in his 1904 book, Radiation and Emanation of Radium. Fall of the Victorian Universe. Early in the 20th century, the long rivalry between the Stoic and Epicurean systems, whose popularity alternated, ended. Over 2,000 years had passed. The limited medieval universe of celestial and angelic spheres developed into a Stoic system of celestial spheres submerged in an initial and enigmatic void in the late Middle Ages. Then, discovered in 1427, the magnificent poem De Rerum Natura exploded on the scene, and Europeans' minds to the vertigo possibility of a huge Epicurean system. Nicholas of Cusa, Thomas Diggers, Giordano Bruno, William Gilbert, and many natural philosophers, Cartesian and Newtonian, were spreading the message. However, the data from the 18th century was contradictory. Eventually, the pendulum swung once more in the 19th century. A one-island Stoic system was then the accepted model of the universe. Early in the 20th century, the old argument surfaced. Are we living in a one-island or many-island universe? 1918 overthrew the Herschel galactocentric system. Harlow Shapley, 1885-1972, was an American astronomer investigating the distribution of globular clusters, or compact clusters of ancient stars. These clusters, he discovered, create a spherical distribution with their center tens of thousands of light-years distant in the Sagittarius constellation's direction. The globular clusters, Shapley noted that the globular cluster belongs to our galaxy, implying that the galaxy's center is also the center of their distribution. A light-year is the distance light travels in 1 year and equals 63,000 astronomical units. Dutch scientist Jan Oort verified this finding. Astronomers verified this by demonstrating that Milky Way stars are orbiting somewhat around the far-off center. Early in the 1920s, Shapley supported the one-island universe, while Heber Curtis, another American astronomer, supported the many-island universe. Shapley overestimated the distances of the globular clusters and made the galaxy much too large because of inadequate allowance for absorption of starlight by interstellar dust. Curtis underestimated the distances of the stars and made the galaxy much too small. Shapley defended the Victorian vision of a massive galaxy until 1930, finally giving up. Referred to by some as the Great, this intellectual struggle concluded the protracted conflict between the competing Stoic and Epicurean systems. The debate came out in favor of an Epicurean-style system first proposed by ancient atomists. Still a conundrum. Our galaxy looked far bigger than other galaxies. In 1952, Walter Baade cracked the riddle by differentiating between the Cepheid variables of these two stellar populations and between population I and the two stars, chapters 5 and 6. The Milky Way no longer seemed disproportionately huge, and this had the effect of doubling the distances and sizes of other galaxies. Reviewments. One could say that the scientist and philosopher Immanuel Kant of Königsberg released a thorough philosophy under critique of pure reason in 1781. Kant's perspective holds that an activity of a priori, subconscious, ideas of primitive origin arranges the world of sensations into meaningful perceptions. From all past events of the species, these basic concepts, from all past experiences, are indispensable for understanding our present and disjointed world of sensations. In Kant's philosophy, the ideas that structure our experiences belong to our own minds. In Plato's philosophy, they belong to the universal mind. 2. William Herschel claimed that botany and astronomy have much in common. He penned a paper titled On the Construction of the Heavens. This method of viewing the heavens seems to throw them into a new kind of light. They are now seen to resemble a luxuriant garden, which contains the greatest variety of products, options in different flourishing beds. And one advantage we may at least reap from it is that we can, as it were, extend the range of our experience to an immense duration. For, to continue the simile borrowed from the vegetable kingdom, is it not always the same thing? whether we live successively to witness the germination, blooming, foliage, fecundity, fading, withering, and corruption of a plant, or whether a vast number of specimens selected from every stage through which the plant passes in the course of its existence be brought at once to our view. To learn how an oak tree grows, we do not study a single oak in isolation growing over a long period, but many oaks in a forest in different stages of growth. Similarly, with stars. Richard Proctor, in Our Place Among the Infinity, 1876, noted William Herschel's change in cosmological ideas. As the work progressed, Sir William Herschel grew less confident. He began to recognize signs of the complexity of structure, which set his method of stargazing at defiance. It became clearer to him, as he extended his survey, that the star depths were, in fact, unfathomable. The main goal of observational astronomy is the compilation of catalogues declaring positions, descriptions, and spectral composition. French astronomer and enthusiastic comet hunter Charles Messier, 1730–1817, assembled a catalogue of 103 nebulae. The Messier nebulae are perfected with the letter M. Thus, M1 is the Crab Nebula, described as whitish light and spreading like a flame, and M31 is the galaxy in Andromeda. He did this so astronomers would not confuse these same nebulae with comets just beginning to shine. William Herschel produced catalogues, including descriptions of thousands of nebulae and listings of positions. John Herschel carried on this work, and in 1864 he produced the General Catalogue, GC. Comprising 5,000 nebulae and star clusters, this was the first methodical survey of the whole sky. The new General Catalogue, NGC, took over from the GC in 1890, and later supplements, index catalogues, were added. The galaxy M31 is hence sometimes referred to as NGC 224. Whether accurate or not, this narrative shows a difference between theism and deism. Napoleon Bonaparte, Emperor of the French, reportedly told Laplace concerning his celestial mechanics, "You have written this huge book on the system of the world without once mentioning the author of the universe." Laplace responded, "Sire, I did not need that hypothesis." Deism arrived in the Age of Reason and is the belief that God created a self-running universe. Theism is the old belief that God created and ran the universe. Laumer was a deist. Newton was a theist. 5 hierarchical astronomy evolved into respect. Able to be a major contender when John Herschel and Richard Proctor presented it as a night riddle's answer. Early 20th century Swedish astronomer Carl Charlier and Irish physicist Fournier Dalbe in England embraced this concept. Widely publicized work by Charlier demonstrated that stars do not cover the sky, and the sky at night is dark if the density of the clusters dropped suitably rapidly with increasing size, corresponding with a fractal dimension of 2 or less. Fournier Dalbe proposed the hierarchical theory whereby the visible universe is only one of a sequence of universes, including solar systems of increasing size, arranged so that the atoms in one universe are the atoms in the next higher universe, and so on. He demonstrated how the nighttime sky is black in worlds created this way. Astronomers sometimes refer to a hierarchy as the assembly of stars into galaxies, galaxies into clusters, and clusters into superclusters. Strictly speaking, this is a word misused. Usually, but not always, a hierarchy is a pecking order arrangement, whereby each member subordinates those below and follows those above. Usually, these consist of human beings. Large corporations and government agencies are hierarchies. With its angelology and demonology, the medieval universe was also hierarchical. According to Kant and Lambert, the technically accurate term for hierarchy is multi-level. A complete multi-level universe, an inbound number of levels in an inbound universe, has an ultimate cosmic center at the highest level. Still, this center is far away, and its reality is up for discussion. Fournier-Dalbé and Charlier demonstrated that in a multi-level universe, the total mass of matter is far less than that of a homogeneous one. Higher and higher levels steadily cause the mass and volume of the clusters to rise. For clusters to remain apart from one another, their volume must increase more quickly than their mass. On ever bigger scales, the average density, mass divided by volume, gradually falls. The density of matter averaged over an infinitely large scale in an in situ multi-level universe is vanishingly small. Stars, star clusters, galaxies, galaxy clusters, and superclusters together make a finite hierarchy. That is, a finite number of levels, that best captures the observed universe's clumpiness. Though this is yet unknown, the universe might be homogeneous in size beyond superclusters. 6 is studying whatever reaches Earth, which helps us to know the heavens. Old astronomy used optical observations accompanied by color descriptions. Observations in the new astronomy were optical with spectral decomposition. Observations in modern astrophysics comprise all electromagnetic radiation: radio, microwave, infrared, optical, UV, X-ray, gamma ray, particle radiation, cosmic ray and neutrinos, and meteorites. Before the new astronomy, everyone thought that star chemical composition was permanently unknown. French mathematician, philosopher, and humanist Auguste Comte said in his Cours de philosophie positive, 1830-1842, "Any research that cannot be reduced to actual visual observation is excluded where the stars are concerned. We can see the possibility of determining their forms, distances, magnitudes, and movements. But it is inconceivable that we should ever be able to study, by any means whatsoever, their chemical composition or mineralogical structure." 7. The observatory became a meeting place where terrestrial chemistry was brought into direct touch with celestial chemistry. William and Margaret Huggins, Atlas of Representative Stellar Spectra. An unsigned article in a magazine, Good Words, on how to make your own spectroscope launched Margaret Lindsay into the new science of spectroscopy. She was a keen photographer and also an observer of the heavens with instruments she made. By chance, she met the article's author, William Huggins, who was visiting her hometown, Dublin, to inspect his new telescope, which was manufactured by Howard Grubb. Spectroscopy sparked romance, and in 1875 they married. Working as a team, he with failing eyes and she keen-eyed, they made observations using state-of-the-art photography and spectroscopy that helped launch the new astrophysics science. Queen Victoria in 1897 knighted William by conferring the Order of the Bath for the great contributions which, with his gifted wife, he has made to the new science of astrophysics. Harrison, Darkness at Night. 8 diode. Little attention was paid to the cosmic effects of a limited speed of light AC for an extended period. Every now and then, astronomers note that light moves a finite distance in a finite period. One or two voiced surprise at our seeing astronomical bodies as they were thousands and millions of years ago. Articles, books, and lectures either ignored or dismissed the implication that the universe is at least as old as light's time to travel from its farthest visible regions, maybe because it ran against accepted religious doctrine. Pre-relativity. Victorian days hardly ever revealed the embarrassing idea that when we gaze out into space to the limit of the visible universe, we see things as they were initially. Many British astronomers were Church of England members, and astronomy, the most socially acceptable and religiously accurate of the sciences, was in business, exposing the works of God rather than contradicting scriptural records. In the clockwise universe, God appeared to be only the clockmaker, the being who had shaped the atomic parts, established the laws of their motion, set them to work, and then left them to run themselves. Thomas Kuhn, The Copernican Revolution, 1957. Are you a theist or a deist, by chance? Stated differently, would you rather live in a created, self-regulated clockwork universe, or a universe fashioned and under control by a divine power? 4. Draw a two-dimensional fractal displaying 3 levels and find the fractal dimension d. d less than 2 implies what? Create your own do-it-yourself fractal. Build a 3-dimensional, 3-level fractal from basic objects, toothpicks and tiny rubber balls. Then find the fractal dimension. The fractal dimension is 100 galaxies, each of size 1. 100 clusters form a supercluster of size 100, and so on. What is the size 10 cluster? Kant envisioned a multi-level universe with an in-situ finite number of levels spanning infinite space. Such a universe, he said, has an ultimate center. Still, this isn't very clear. On the most enormous scale is a center possible when the density... The Sun, planets and stars appear far away from Earth. Our closest star, the Sun, is 150 million kilometers, or 93 million miles, distant. Though they are appropriate for measuring distances on the surface of the Earth, kilometers and miles are far too small for astronomical distances. Nearly all of the data from outside space arrives to us in light and other forms of radiation, traveling 300,000 kilometers per second. The Sun was seen 500 years ago. Light from the Sun travels 500 seconds to reach the Earth. We say 500 light seconds separates the Sun from us. The light travel time is the period light moves from a far-off body. When referring to a far-off body, light travel time is a pleasing method of gauging vast distances and has the advantage that we know right away how far back we look into the past. 10 years ago, we saw a star 10 light-years distant, almost 100 trillion kilometers. Looking out into space, we always look back in time. Light travels across the solar system and takes roughly 10 hours, Pluto's orbit's diameter. The great distances to the closest stars several light-years away dwarf our circling planetary system, so vast by conventional terrestrial criteria. Tens of thousands of light-years separate an incredible array of billions of stars. Stars of our galaxy are these ones. Other galaxies at distances of millions of light-years lie beyond our galaxy. Most of these systems comprise billions of stars. Even astronomers who used to consider vast distances are astounded by the extravagant use of space in the architecture of the universe. Time has been used sparingly, so who could wonder at only a few thousand, a few million, or even a few billion years of light travel time? However, the unique units of measurement we apply on Earth lead to this opulence in space and economy in time. Using light travel time as a measuring tool, we set aside our terrestrial inclination of preferring small and large distances. 1 second of light travel time seems so little, yet it is equivalent to 300,000 kilometers, which is quite vast. Just 1/20 of a light second defines the largest distances on the surface of Earth. We live for 70 years. During that time, the Sun, with its planet count, barely covers 20 light days across the galaxy. From a cosmic standpoint, we occupy a small space but remain for a long time. This knowledge helps us to appreciate the vastness of space more than the passing of time. The first approach uses the parallax E effect for stars a few hundred light-years away. When we hold a finger straight at arm's length and observe how it seems to move to and fro when seen alternately with the left and right eyes, the parallax efficacious is rather clear-cut. The neighboring stars are also seen in somewhat different directions from various points on the Earth's orbit around the Sun. Seen from 2 points on the Earth's orbit, 1 astronomical unit apart, a star at 1 parsec points in different directions, separated by an angle of 1 second of arc. Seen alternately with the left and right eyes, a candle flames at 10 miles, 16 kilometers, in different directions, separated by 1 second of arc. Stellar parallax becomes difficult to detect at more than 300 light-years distances. Stars too far away to have a clearly discernible parallax could use the second approach. These far-off stars are chosen for their near resemblance to surrounding stars. Apparent brightness allows one to ascertain the distance of the far-off distant stars from the known distances of the surrounding stars. Every star has an absolute or intrinsic brightness, and an apparent brightness is determined by its intrinsic brightness and distance from Earth. For example, parallax observations show that a given star is 100 light-years distant. Considered to have the same intrinsic brightness as the first star, a second star is seen with less apparent brightness. The second star's apparent brightness is ma100 that of the first star. We derive that the fainter star is at a distance of 1,000 light-years, using the apparent brightness declining as the inverse square of the distance, in the absence of interstellar absorption. Let us depart the planet and wander across space, seeing the many stars. Few stars are quite bright. Most are less luminous than the Sun. Most stars, we also observe, fall into families of 2, 3, or more members. Common double stars, sometimes known as binary systems, are found in almost half of all stars near us. Usually separated by astronomical units, double stars circle each other over many years. Conversely, some double stars exchange matter, have eruptive outbursts, and evolve in amazing and unexpected ways. They are far closer together and have periods of just a few days. Ignoring binary systems, the average separating distance between neighboring stars is roughly 1 parsec. 20 million times the Sun's diameter. This distance is 200 trillion astronomical units. Consequently, about the size of the stars and their planetary systems, the distances separating stars are enormous. Color and brightness. Stars are held together by gravity. They are luminous globes of hot gas pouring radiation into space. Their obvious qualities of great interest are brightness and color. The star's surface temperature controls its color. Its brightness depends on the quantity of light emitted from its surface. The Hertzsprung-Russell diagram, after its originators, or the HR diagram, is the brightness-color diagram for stars. Every point on the HR diagram relates to a specific mix of color and luminosity. With a surface temperature of 5800 Kelvin and a yellow-white hue, the Sun is among Sun-like stars, yellow-white in color and comparable size and brightness. Red and big. Other stars are the red giants with surface temperatures of roughly 3000 Kelvin. Others, white and small, are the white dwarfs with 10,000 and above Kelvin surface temperatures. The surface. The star's surface temperature and surface area determine the brightness, the emission rate of luminous energy. The large surface area of a red giant of low surface temperature causes great brightness. Because of their small surface area, a white dwarf with a high surface temperature has low brightness. A red giant of low temperature and high brightness is like a charcoal fire, a white dwarf of high density. We are often interested in the total amount of radiation emitted by a star, some of which is not visible to the eye. We use the term luminosity for total radiation, visible and invisible. A star's luminosity is usually stated in solar luminosities. When each star is plotted as a point in the HR diagram, we notice that the points are not scattered randomly, but tend to concentrate in certain regions. Most stars, including the Sun, lie in a band called the main sequence that runs diagonally across the diagram. Red stars, low temperature and cool, within the main sequence have low luminosity, and blue stars, high temperature and hot, have high luminosity. All main sequence stars derive energy and maintain luminosity by transforming hydrogen into helium through nuclear reactions. Star masses increase steadily up the main sequence. The less massive stars at the lower end of the main sequence slowly transform or burn hydrogen into helium. The more massive ones at the upper end transform the gas rapidly. Most stars have masses in the range of 110 to 10 times the Sun's mass, surface temperatures in the range of 2500 to 25,000 Kelvin, and luminosities in the range of 1,000 to 10,000 times the Sun's luminosity. On the main sequence, the luminosities of stars vary enormously, but their sizes do not vary significantly. The radius of the most luminous is about 25 times that of the least luminous. An unknown number of stars have masses less than 1/10 the Sun's mass. These dull stars, known as red dwarfs and brown dwarfs, are often the unseen companions of visible stars. A few extreme stars have masses as enormous as 60 times the Sun's and are 10 million times more luminous than the Sun. Such a bright star near Alpha Centauri would shed as much light on Earth as the full moon. They have consumed their central supplies of hydrogen and have quit the main sequence, and their central regions are contracting higher temperatures and density in search of further energy sources. Below the main sequence in the HR diagram are the white dwarf stars. The white dwarfs are approximately Earth-sized. They are dense, hot, and not very luminous because of their huge surface areas. These stars have come to the end of their evolution and are slowly cooling. Large numbers of these dying stars exist. About 10% of the nearby stars are white dwarfs. But they are difficult to find because of their low luminosity. Not all stars terminate their careers as dense white dwarfs. Many continue to evolve and become neutron stars, and as we shall later see, some become black holes. Most stars shine almost constantly, but a small proportion, the variable stars, vary periodically. About a quarter of all variable stars are eclipsing binary systems whose brightness varies, because the orbiting stars pass periodically in front of each other. But the majority are pulsating variables, rhythmically expanding and contracting, pulsating in size and brightness. An important class of pulsating variables consists of luminous yellow giants above the main sequence known as Cepheids. They shine between 100 and 10,000 times as bright as the Sun, and are so named because the first star discovered in this class was Delta Cephei, a faint star, seen with the naked eye in the constellation of Cepheus. Our galaxy is home to over 700 Cepheids, most of which have pulsation periods ranging from 3 to 50 days, and some exhibit brightness variations as high as 5. Polaris, the pole star, is a Cepheid that changes brightness by 10% for 4 days. Cepheids are more massive stars than the Sun and have evolved beyond the red giant state. Cepheids release trapped radiation more easily through oscillation. Cepheids are important because they serve as distance indicators. We know that their oscillation periods correlate with their luminosities. The higher the luminosity, the longer the period. This period luminosity relation was discovered in 1912 by the astronomer Henrietta Leavitt of the Harvard College Observatory. By checking how long it takes for a Cepheid to change brightness, an astronomer can find out how bright it is using the period luminosity relation, and then figure out how far away the Cepheid is by comparing its true brightness to how bright it looks from Earth. Distance determination is always difficult in astronomy, and this neat method explains why the relatively rare Cepheids are important stars. Stars are globes of hot gas that radiate energy away into space. This energy, emitted from the surface, originates in the deep interior and diffuses slowly to the surface. Heat flows from hot to cool regions. Hence, the center of a star is much hotter than its surface. The central temperatures of stars are enormous. In the Sun, for example, the central temperature is around 15 million Kelvin. The central temperatures of stars increase in the main sequence, going from low-mass to high-mass stars. Self-gravitation holds stars together. The gravitational force pulling inward is opposed to a force pushing outward. The outward pushing force is the pressure of the hot gas in the interior. Without pressure inside the Sun, it would collapse in only 1 hour and become a black hole. The balance of pressure, the pressure gradient, and gravity is easy to understand. Consider a star's imaginary shell consisting of two spherical surfaces. The pressure on the shell's inside surface pushes outward, and the pressure on the outside surface pushes inward. This formula is the hydrostatic equation for a star. The star consists of many imaginary concentric shells, and as we proceed inward, the pressure rises each time a shell is crossed. The pressure progressively increases and attains its maximum value at the center. The central pressures of stars are enormous. In the Sun, for example, the central pressure, force per unit area, is equivalent to a weight on Earth of 100 million tons, resting on an area equal to that of a dime. Why is the temperature high? The Sun's average density is 1.4 grams per cubic centimeter, or 1.4 times the density of water, and its central density is approximately 150 grams per cubic centimeter. Nothing in the normal solid or liquid states can support the crushing pressure inside the Sun. A dense and hot gas is the only possible form of matter under these conditions. A gas at a temperature of millions of degrees is unlike any ordinary gas we know. The atoms move at high speeds, hundreds of kilometers per second, and their frequent and energetic encounters with one another strip away their electron clouds. Hence, most atoms tend to be fully ionized, all their electrons removed. And the gas consists of negative electrons and positive atomic nuclei moving freely as independent particles. The radiation within this hot and dense gas consists not of the gentle, beneficent light emitted from the comparatively cool surface, but of intense X-rays. Each ray of this intense radiation in the deep interior travels on average 1/10,000 of a centimeter before it is captured or deflected by gas particles. Pressure in such gas is proportional to density multiplied by the temperature, and the high central temperatures in stars result from the large pressures needed to support stars against their internal pull of gravity. Thus, we understand why stars are luminous. Their interiors are hot because of the high pressure needed to withstand gravity, and the radiation in the high-temperature gas slowly diffuses to the surface and escapes into space. Nuclear reactions replace the lost energy and maintain the stars in a luminous state for long periods. Stars are luminous not because of nuclear energy, but because their great masses require high internal pressures. The radiation inside a star is continually scattered by gas particles, and its outward flow to the surface is greatly impeded. It takes about 20 million years for radiation to diffuse from the center to the surface of the Sun. If nuclear energy generation suddenly ceased in the center of the Sun, we would not know that anything serious had happened until 20 million years later. Convection and sound waves. Impedance to radiation's flow is opacity. When the opacity rises, the gas often absorbs interior radiation, and convection transports the energy. Gas is stirred into motion, and ascending and descending currents carry energy as heat toward the surface. The Sun's outer layers, or envelope, have high opacity, and radiation cannot easily reach the surface by diffusion. This procedure throws the envelope of the Sun into a state of convection, much like the water in a boiling kettle, and heat is transported to the surface. Stars of smaller mass than the Sun have deeper convective envelopes, and stars more than twice the Sun's mass lack convective envelopes, but have instead convective cores. In the more massive stars, nuclear energy is released in a small central region, and the core is thrown into a convective state because the radiative transport of energy is too slow. The song of a star outrival is the song of the humpback whale. The star's interior is filled with a symphony of sound, ranging from deep, reverberating rumblings to quivering, high-pitched shrieks. Nobody has told a star what size and shape it must be, with what brightness and temperature it must shine, or how it must find the energy continuously lost from its surface. Sound waves travel through a star, such as the Sun, in about 1 hour, and by making ceaseless adjustments, with each part sending out sound waves to all other parts, the star seeks each moment to rediscover its natural equilibrium state. At the lowest vibration modes, the star constantly heaves and groans. At the other extreme, at the highest modes, 60 octaves higher, it is filled with the hiss of high-speed particles frantically jostling one another. Heliosismology, the study of the vibrations of the Sun's surface, reveals much of the Sun's interior structure. The Sun acts as an immense loudspeaker. Its density decreases steadily from the center to the surface, and each sound wave grows in amplitude as it travels outward like a whiplash. An amplified torrent of sound reaches the surface, passes through and dissipates in the outer thin atmosphere. In the case of the Sun, with its noisy convective envelope, this dumping of acoustic energy raises the corona, the upper solar atmosphere, to a temperature of 1 million or more degrees Kelvin. Because of its low density, the corona cannot radiate away the energy it receives, and it does the only thing possible. It expands and carries the energy with it. The corona is like a giant jet engine. It sucks in gas from the Sun, and the gas, heated by acoustic energy, blasts away at high speed. This energy is the outward streaming solar wind that carries away 100 billion kilograms of gas each second at a speed of several hundred kilometers a second. Other stars also have stellar winds generated by their internal acoustic tumult. Occasionally, these stellar winds are much stronger than the solar wind, and some stars blow themselves away on a time scale of millions of years. Stars are immense nuclear reactors that generate nuclear power. The sunlight that falls on the Earth's surface originates as nuclear energy deep within the Sun. We shall take a detour to understand how stars generate nuclear energy. Atoms combine to form molecules, which are held together by electrical forces that result from atoms sharing or exchanging their outermost electrons. The assembly and rearrangement of atoms in molecules release chemical energy. Most of the energy humans use originates from the combustion of chemical materials such as wood, coal, oil, and gas. Each atom has a small positively charged nucleus surrounded by a comparatively large cloud of negative electrons. The nucleus itself consists of heavy particles called nucleons that are either protons or neutrons. Protons are positively charged, and neutrons have similar mass but no electrical charge. The nucleons in a nucleus are held together by strong nuclear forces. When nucleons are added, removed, or rearranged in atomic nuclei, they either release or absorb nuclear energy, usually millions of times more than the chemical energy released by adding, removing, or rearranging atoms in molecules. Ancient alchemists sought a way to transmute the elements, and we have now realized their dream. Nuclear reactors transmute the elements, not to produce gold from baser metals, but for research and the release of nuclear energy. Imagine that we have a supply of free nucleons that we combine in various ways to produce the atomic nuclei of the chemical elements. Each time a nucleus is constructed out of free nucleons, regardless of what kind of nucleus it is, energy is released because nucleons attract one another with strong, short range. Nuclear forces. The total energy released in the construction process is the binding energy of the nucleus. All discrete things have binding energies of one kind or another. A stone is bound to the Earth by gravity, and its binding energy is released when it falls from outer space, enters the atmosphere, and strikes the Earth's surface. The attractive force in this case is gravity. The attractive forces between the atoms in a molecule are electrical. The attractive forces between nucleons in a nucleus are the strong force or the strong interaction. When we assemble something, we release its binding energy. When we disassemble it, we expend the same energy to break it apart. It is more convenient to think of the binding energy per nucleon, that is, the total binding energy of the nucleus divided by the number of nucleons. Binding energy per nucleon rises rapidly at first for the light nuclei, then slowly increases for nuclei of greater atomic weight, reaches a maximum at iron, which has 56 nucleons, and thereafter steadily decreases. For instance, starting with 224 free nucleons, 4 iron nuclei release more energy than one radium nucleus with an atomic weight of 224. Fusion and fission. Normally we cannot begin with free nucleons. Protons, the nuclei of hydrogen atoms, are easy to find, but neutrons are scarce because they decay and have a lifetime of only 10 minutes in their free state. We must use existing nuclei by either putting them together, a process known as fusion, or breaking them apart, a process known as fission. The nuclear energy game aims to increase binding energy. The prize is the energy released. When moving from the left, energy comes from the fusion of light nuclei into heavier nuclei. When moving from the right, power comes from the fission of heavy nuclei into lighter nuclei. Stars obtain their energy from the fusion of light nuclei. Earth now obtains nuclear energy by splitting the heavy uranium and plutonium nuclei. Barrier penetration. A star on the main sequence generates energy by slowly converting hydrogen into helium. Nuclear reactions release this energy slowly in the star's central region and diffuse toward the surface. Why do stars release nuclear energy gradually? Why doesn't it happen suddenly, releasing an immense explosion of energy like a nuclear bomb? The explanation is readily comprehensible. Protons are positively charged, and their electrical repulsion is a barrier preventing them from coming close together. Positively charged protons in the deep interior of a star rush around at speeds of hundreds of kilometers a second. They continually approach one another, yet, because of their electrical repulsion, rarely come close enough to engage in nuclear reactions. We have considered protons as if they were bodies, just like stones. This is a misleading mechanistic picture. Often, atoms are portrayed as miniature solar systems, with electrons moving in orbits about the nucleus, like planets moving around the sun. This similarity is a misleading picture that fails to reveal the beauty and intricacy of the subatomic world. All subatomic particles, such as electrons, protons, and neutrons, behave like waves in space. These vibrating waves form many patterns. Thus, electron waves, waltzing about the nucleus, determine the size and properties of each type of atom. Protons, like electrons, behave as waves, but their wavelengths are much smaller than the wavelengths of electrons. This feature explains why the nucleus that contains nucleon waves is so small. All particles have corpuscular and wave-like properties and often behave strangely, unlike familiar bodies such as stones. A stone thrown against a wall usually rebounds, whereas a wave, like a radio wave, may penetrate the wall and emerge on the other side with diminished intensity. Because of its wave-like nature, a particle like a proton may penetrate a wall. This procedure takes us into quantum mechanics, where corpuscles are what we see and waves explain what we see. Because of its wave-like nature, a particle is spread out in space, and the chance of finding it in its corpuscular form at any point is proportional to the square of the wave amplitude. Where the wave amplitude is largest, there is the best chance of finding the particle as a discrete entity. A particle, such as an electron or a proton, spreads itself out in space in the form of waves. When the particle is detected, the waves collapse, and the particle assumes the observed corpuscular form. Of course, we cannot have only a bit of a particle. And in the corpuscular form, it must always be either the whole particle or nothing. Consider what happens when a proton encounters a barrier, such as the electrical repulsion barrier between it and another proton. The barrier partially reflects and partially transmits the wave. Suppose the wave's amplitude after penetration is only 1/10 of the original incident amplitude. The chance of finding the particle is proportional to the amplitude square. Therefore, the chance of finding it on the other side of the barrier is 1/100. It is impossible to have 1/100 of a particle on one side of the barrier and 99/100 on the other. Therefore, we say the chance of penetration is 1/100, and of every 100 participants striking the barrier, 99 are reflected and 1 is transmitted. The hang-ups. The first hang-up is the repulsion barrier. At each encounter between protons, a small chance exists of a wave-like penetration of the electrical repulsion barriers. Even in the center of the Sun, where the temperature is high and protons move fast, the chance of penetration is small. Each proton makes head-on collisions with other protons about 1 trillion times a second. And about once every second, it penetrates a repulsion barrier and comes face-to-face with another proton. The second hang-up is the weak interaction. Once protons meet face-to-face, after penetration, they take a long time to react together. Before they decide they like each other, they separate and go their respective ways. Once in 10 billion years, on average, each proton in the center of the Sun comes face-to-face with another proton, and together they react violently. Energy is released, transforming into a joint particle known as the deuteron. The deuteron contains 1 proton and 1 neutron, and forms the nucleus of the heavy hydrogen atom. Heavy hydrogen is known as deuterium. The deuteron quickly picks up another proton. The second hang-up no longer applies, and with more energy release, becomes a helium-3 nucleus containing 2 protons and 1 neutron. Helium-3 nuclei then quickly combine with the release of more energy and become the helium-4 nuclei of ordinary helium atoms. The nuclear reactions described are known as the proton chain, in which 4 protons, step by step, become 1 helium nucleus. 2 main hang-ups exist. First, positively charged protons have difficulty in penetrating their repulsion barriers. Second, neutrons are slow to engage in a nuclear reaction with each other even after penetration. This second hang-up exists because a weak interaction is involved that transforms a proton into a neutron and requires the creation of a positron, a positive electron that is the antiparticle of the common negative electron, and a neutrino that has little or no intrinsic mass and moves at or close to the speed of light. Elements heavier than helium, such as carbon, oxygen, nitrogen, and so on, add up to 1 to 2% of the matter in stars, like the Sun. In main sequence stars, a second method of converting hydrogen into helium, the carbon cycle, works as follows. A carbon-12 nucleus combines with a proton and transforms into nitrogen-13, which decays and becomes carbon-13. The carbon-13 nucleus combines with a second proton and transforms into nitrogen-14. The nitrogen-14 nucleus combines with a third proton and transforms into oxygen-15, which decays and becomes nitrogen-15. The nitrogen-15 nucleus finally combines with a fourth proton and produces nitrogen-16, which is unstable and immediately splits into a carbon-12 nucleus and a helium-4 nucleus. Energy is released at each carbon cycle step, transforming 4 protons into 1 helium nucleus. The carbon-12 nucleus acts as a catalyst and is not consumed. The electrical barriers of carbon-12, carbon-13, nitrogen-14 and nitrogen-15 are tougher to get through than those in the proton-proton chain, making it harder to move forward in the carbon cycle. However, once the proton gets past the barrier in the carbon cycle, it is much easier for it to react because there is no weak interaction happening during the quick moment when the proton meets the nucleus. In the carbon cycle, there is thus a trade-off in hang-ups. The first increases and the second decreases. In lower main sequence stars, including the Sun, The proton chain dominates. In upper main sequence stars, the carbon cycle dominates. Upper main sequence stars have higher central temperatures. In these stars, protons penetrate the substantial repulsion barriers of carbon, oxygen, and nitrogen nuclei more easily. James Jeans, a physicist, proposed early in the 20th century a general theory of fragmentation. Initially, he argued, the universe was filled with chaotic gas, and astronomical systems were formed in succession by a process of fragmentation of nebulae out of chaos, of stars out of nebulae, of planets out of stars, and of satellites out of planets. We still think the universe is fragmented into galaxies. Galaxies are fragmented into stars, but we no longer believe that stars fragment into planets, and we doubt that planets normally fragment into satellites such as the Moon. The majority of stars in our galaxy formed long ago, but many are young because new stars are still being born at a rate of 1 or 2 each year. They are born in the large and dark clouds of gas in interstellar space. These dark clouds consist of hydrogen and helium and contain a small amount, 1 or 2% by mass, of heavier elements, mostly dust grains. Very young stars are still close to their birthplaces, surrounded by the tattered remnants of clouds from which they were born. Like the Pleiades, young stars can cluster and be born from the same dark cloud. Origin of the solar system. The solar system comprises the Sun, the Earth, and other planets. It was born approximately 5 billion years ago, when the universe was between 1/3 and 1/2 of its present age. We can imagine that the Sun began as a blob, a denser part of a cloud where other blobs formed into stars. The blob became a globe of gas and dust, a protostar, dark and cool, typically twice as massive as the present Sun. It consisted of hydrogen gas, about 25% helium by mass, and all the heavier elements amounted to 2%. In a speculative vein, we use the present tense as if we were there watching the scene. The globe of gas rotates, and D at Furs is more or less spherical. But as the globe contracts, it rotates faster and slowly flattens and becomes oblate. The central region, the core, contracts faster, gets denser, and hence spins faster than the outer regions of the globe. Contraction of the core eventually slows down because of the effect of centrifugal force. The result is a viscous drag that acts like friction. Because the central regions rotate relatively fast, the globe consists of layers of gas moving at different speeds, rubbing against one another. This rubbing acts as a braking mechanism that slows the spinning core and transfers its rotation to the outer regions of the globe. The core continues its slow contraction to higher densities using viscous forces and the action of magnetic fields. Outside the central region or core, the gas remains moderately cool, and its chemical elements, heavier than hydrogen and helium, tend to consolidate into dust grains. These dust grains, usually about 1/1000th of a millimeter in diameter, repeatedly collide and begin to stick together. They aggregate and form small pieces of meteoroidal rock and ice. More than 50% of this meteoroidal material is in the form of ices of frozen water, ammonia, and methane. And the rest consists of chemical elements, such as metals and their oxides and silicates. When many meteoroids have grown and become pebble-sized, they move more or less freely through the gas and behave like tiny planets. But the friction of their motion through the gas causes their orbits to become circular and to settle into a flat disk. Within this thin rotating disk of matter, which lies inside a thick rotating disk of gas, the meteoroids ceaselessly jostle one another and either break into smaller pieces or coalesce to form larger chunks of matter. This process is a game of survival of the biggest. The bigger the meteoroid, the more it eats up, the smaller the meteoroid, and the less likely it is to be shattered by collisions. The large meteoroids grow into planetesimals hundreds and thousands of meters in diameter. There is always a downpour into the disk of newly formed meteoroids. The planetesimals occasionally collide and dissolve into far-flung fragments or aggregate into larger bodies. In the planet's struggle for survival of the biggest, the victors sweep up all they encounter and become the protoplanets. The protoplanets, massive, Earth-like bodies, attract and begin to retain the gaseous elements of the globe and acquire atmospheres rich in hydrogen and helium. These atmospheres grow, and the protoplanets become large planetary gas spheres, unlike Jupiter and Saturn. Meanwhile, the core of the globe becomes dense and hot and begins to approach its final state. The primordial sun, blanketed from view by swirling gas and dust, has disrupted that by fusing hydrogen into helium. It has access to an immense reservoir of nuclear energy. It becomes convulsive, a flaring T Tauri-type star seeking to find an internal structure that matches the rate at which nuclear energy is released in the center to the rate at which energy is lost from the surface. T Tauri is an irregularly varying star surrounded by gas and dust, and is evidently a newborn star approaching the main sequence. Similar stars are referred to as T Tauri-type stars. As it approaches the main sequence, the primordial sun is in an eruptive state, and, from its upheavals, issues an intense wind of fast-moving gas that rushes outward and carries away large quantities of matter. The fierce wind and brilliant radiation from the newborn sun thrust the remnants of the gaseous globe back into interstellar space. Now commences a final struggle between the planets and the sun. The planets try to hold on to their massive atmospheres, while the bright sun, with its fierce wind, tries to strip away these atmospheres. The inner planets, Mercury, Venus, Earth, and Mars, lose the struggle and are stripped down to their rocky cores. The outer planets, Jupiter, Saturn, Uranus, and Neptune, win because of their greater distances and retain their lighter elements forever. The sun at last settles down into a quiescent state. However, the solar system is cluttered with debris from the birth process. Scattered planetesimals encircle the sun and the planets in enormous numbers, and hordes of meteoroids drift into interplanetary space. The mopping up of this debris by the sun and planets is at first rapid and slows down after several 100 million years. This is the bombardment era that lasts for roughly 500 million years. The results of this era of intense bombardment are still visible on the surface of the Moon. Tens of thousands of surviving planetesimals, the asteroids, still exist between the orbits of Mars and Jupiter. Apparently, they failed to amalgamate into a planet. Several other planetesimals survive as moons distributed about the various planets. The inner planets have 3, of which the Moon is the largest, and the outer planets have at least 29. Stars less massive than the Sun evolve slowly and stay on the main sequence longer than 10 billion years. Many low-mass stars have not become appreciable in our galaxy's lifetime. But more massive stars evolve quickly, and according to their masses, terminate as white dwarfs, neutron stars, or black holes. Here, we consider briefly the fate of these more massive stars. After a star consumes its central hydrogen supply, it leaves the main sequence and moves toward the red giants in the HR diagram. The core now consists almost entirely of helium and has ceased to generate nuclear energy. However, the hot surface of the star continues to lose radiant energy, draining from the central core. In response, the core does the only thing possible. It contracts to a higher density, thus releasing gravitational energy. Because of this contraction, the temperature of the core rises. Two things begin to happen. First, hydrogen just outside the helium core begins to burn. Surrounding the core, a hydrogen-burning shell develops and helium production continues and steadily adds mass to the helium core. Second, the energy released by the contraction of the core and hydrogen burning in the surrounding shell causes the envelope to expand. As the core contracts, the star swells up, and the distended envelope becomes partly convective. The star, luminous, large, and cool, is now a red giant. Once a star leaves the main sequence, it has entered old age with little time to live. It realizes too late that its life in the main sequence has been dull and sedentary, and it resolves to have one last glorious moment before it dies. But not much nuclear energy remains. Burning hydrogen into helium has consumed 80% of the available atomic energy, and drawing on the remaining reserves requires the prodigious feat of burning helium step by step to nickel and iron. At each step, higher temperatures and densities are needed. Hence, the star grows in luminosity, and its diminishing nuclear reserves are consumed at an increasing rate. White dwarfs. We consider an evolved star less massive than 2 solar masses. Its core continues to contract during the red giant phase until, after millions of years, its density and temperature are sufficient to burn helium into carbon. The ignition of helium burning occurs abruptly at a temperature of roughly 100 million Kelvin, referred to as the helium. An intense stellar wind builds up, and either at this stage or a little later, depending on the mass of the core, the star throws off its distended envelope and the bright, naked core is all that remains. Contraction ceases, nuclear burning ends, and the core settles down as a white dwarf. The star consists of an ejected gaseous remnant called a planetary nebula and a slowly cooling white dwarf that has a size approximately equal to that of the Earth. In about 5 billion years, the Sun will become a white dwarf and shine in the sky as a pale light for several billion years while slowly cooling. Supernovas. We next consider what happens to a more massive star. It consumes its central hydrogen supply more rapidly and lives on the main sequence for only a few 100 million years. It then becomes a short-lived monstrous red giant. The helium core, surrounded by a hydrogen-burning shell, contracts to higher density and temperature. Soon the helium begins to burn into carbon and oxygen. The star now has a core of carbon and oxygen, surrounded by a helium-burning shell and an outer hydrogen-burning shell. The star evolves beyond the red giant stage, becomes even more luminous, passes through spasms of pulsation, and ejects large quantities of gas into space at high speed. The core continues to contract to meet the ever-growing demand for more energy. When the central temperature exceeds 3 billion Kelvin, and the density approaches 1 million grams per cubic centimeter, the carbon and oxygen burn progressively, stage by stage, to neon, magnesium, silicon, phosphorus, sulfur, and so on, to nickel and iron. But the nuclear energy released in this multitude of reactions soon radiates away. In these latter stages of advanced evolution, an additional energy loss has emerged and has steadily increased. Hordes of neutrinos, produced in the core by nuclear reactions and the high-temperature gas, stream out through the star in vast numbers. The neutrino luminosity of the core rises and exceeds the radiation luminosity of the surface. Gravitational energy remains, and the core contracts faster to meet the growing energy loss. The central density and temperature soar, and energy spills over and drains away into the production by the fusion of elements heavier than iron. The star is seconds away from death. Neutrinos no longer easily escape from the star. Instead, they diffuse outward from the core and transport energy that heats and ignites nuclear reactions in the hydrogen-rich outer layers of the star. The inward-falling core crushes its heavy elements into helium, and the energy previously acquired by the fusion of light elements into heavier elements must be paid back by releasing further gravitational energy. The neutrino output from the core intensifies and becomes a blast that lifts the exploding envelope and hurls it into space. During the last brief moments of the imploding core, helium is crushed into free protons and neutrons, and all the energy that was radiated for millions of years, while on the main sequence, must be paid back immediately. The core obtains this energy through a final catastrophic collapse. The electrons are squeezed into the protons, and together they become neutrons. The collapsed core, divested of its envelope, emerges as a neutron star. The titanic blaze of energy unleashed by the imploding core and exploding envelope results in a supernova that shines as bright as all the stars in a giant galaxy for a short time. A supernova near Alpha Centauri would be as bright as the Sun. Neutron stars and black holes. A neutron star has a little more than 10 kilometers radius and a density of nearly 1,000 trillion grams per cubic centimeter. A thimbleful of neutron matter would weigh 1 billion tons on Earth. The neutron star has a magnetic field of 1012 Gauss, 1 trillion times stronger than the Earth's magnetic field, and at first rotates rapidly at hundreds of revolutions per second. The star is dead. Long live the star. A pulsar emerges from the ashes of the old star, pulsating across space with a pulse-like message of matter under extreme stress. For 1 million years, the pulsar radiates away its rotational energy electromagnetically, turning more slowly. Neutron stars have masses less than 3 times the Sun's mass. And this limit exists because neutron matter cannot withstand the gravitational pull of greater masses. The imploding cores of more massive stars may not terminate as neutron stars, but continue to collapse and become black holes. In this case, they must enclose themselves within their own curve.